Hello there and welcome to Life Beyond Seen, where curiosity gets comfortable, and the deeper corners of our world are explored slowly, carefully and without hurry. Tonight we are travelling to a place that looks, at first glance, like a lake. A very large lake, certainly, a cold one, a distant one, but still just a lake. And yet, the more scientists study it, the less simple it becomes. It rests in southern Siberia, long and narrow like a scar across the land. In winter, it freezes so solid that trucks can drive across its surface. In summer, it looks calm enough to reflect the sky with almost unsettling clarity. From the shore, you might see nothing more threatening than rippling water and distant mountains softened by mist. It does not roar like a volcano. It does not blaze like a desert. It does not spiral like a hurricane. But Lake Baikal has a way of making researchers uneasy. Not because it is loud, because it is deep. Before we go any further, I am curious. Where are you listening from tonight? Are you somewhere warm, perhaps wrapped in a blanket? Or is there a chill outside your window? And what time is it where you are right now? Early evening? The quiet middle of the night? Morning light just beginning to touch the glass? There is something fitting about discussing a place that has existed for millions of years, while you sit in your own small moment of time. If you find this journey calming or intriguing, or simply a steady voice to accompany the end of your day, I would be grateful if you gave the video a like and perhaps subscribed. It helps this quiet corner of curiosity reach others who might also enjoy exploring strange places at a gentle pace. Now, Lake Baikal. Scientists often describe it using superlatives, and not casually. It is the deepest lake on Earth, the oldest lake on Earth, the largest freshwater lake by volume on Earth. Those are impressive titles, certainly, but impressive is not the same as unsettling. The unease comes from what those records imply. To stand at the edge of Baikal is to stand beside water that is older than many mountain ranges. Water that has collected stories of climates long gone, species long extinct, and geological processes that are still unfolding beneath its surface. This is not a stagnant pool left behind by glaciers. It is not a temporary basin carved by recent ice. It is alive in a slow tectonic way. The lake sits within what geologists call a rift zone. That means the Earth's crust there is pulling apart, very slowly, millimetre by millimetre each year. The land on either side is separating, and in that widening space Baikal rests, deepening. Most lakes fill a depression and remain roughly the same. Baikal is different. It is both filling and sinking at the same time. Sediment gathers at the bottom, layer upon layer, recording ancient history like pages in a book. But beneath that sediment, the crust continues to stretch and thin. The basin grows deeper as the continents gradually part. In a distant future, millions of years from now, this region could become a new ocean. That is not speculation for dramatic effect. It is a measurable geological trajectory. When scientists lower instruments into Baikal, they are not just measuring water depth. They are measuring the slow birth of something far larger. And depth is where the strangeness begins to take on scale. At its deepest measured point, Lake Baikal reaches about 1,642 metres. That is over a mile straight down. If you were to place the tallest building in the world inside it, there would still be water above the roof. But even that number does not tell the full story. Because beneath the water lies sediment. Thick sediment. More than 7 kilometres of it in some places. If you combine the water and the sediment together, the full geological depression beneath Baikal is one of the deepest continental rifts on the planet. In terms of sheer vertical distance from the surrounding mountaintops to the deepest sediment layers, it rivals ocean trenches. Yet it is not an ocean, it is fresh water. That combination alone makes scientists pause. Oceans behave in certain predictable ways. They circulate heat globally. They connect ecosystems across vast distances. Their chemistry is relatively stable, a freshwater body that deep behaves differently. The pressure at Baikal's bottom is immense. Temperatures remain near freezing year-round. Light does not penetrate anywhere near the lowest layers, and still, life exists there. Not sparse life, unique life. Over half of the species found in Lake Baikal exist nowhere else on Earth. Isolation has allowed evolution to experiment quietly for millions of years. Sponges that grow in branching forests beneath the surface, tiny crustaceans that filter the water so effectively that Baikal is astonishingly clear. Fish that have adapted to cold, dark depths with almost translucent bodies. The lake's clarity is another unsettling detail. In some areas, visibility can reach 40 meters. That level of transparency in such a massive and deep body of water is rare. It suggests a delicate ecological balance maintained by microscopic organisms constantly filtering impurities. It looks pure, but purity at that scale is fragile. Scientists worry not only about what Baikal contains, but about how stable it truly is. Climate change is altering temperature patterns across Siberia. Permafrost is thawing. Rivers feeding the lake are shifting in flow. Industrial activity has encroached along certain shores. Pollution has entered in subtle ways. When you combine an ecosystem millions of years in the making with rapid modern change, uncertainty grows. And uncertainty in science is often more unsettling than danger. There are other observations that raise quiet concern. In winter, when the lake freezes over, strange circular patterns sometimes appear in the ice. Massive rings, kilometers wide, visible from satellites. They are not decorative frost patterns. They are linked to warm water currents rising from below, likely driven by underwater hydrothermal activity. Hydrothermal activity in a freshwater lake. That alone shifts the mental image. We associate hydrothermal vents with deep ocean floors, with black smokers and strange tube worms, but Baikal hosts its own versions of geothermal features. Warm plumes rise from cracks in the lakebed, altering local chemistry and possibly influencing ice formation far above. Divers have reported odd sensations descending into Baikal's depths. Not paranormal experiences, not myths, just the awareness of descending into something vast and cold and very, very old. Submersibles have captured footage of steep underwater slopes, rocky outcrops, and sediment plains that stretch into darkness. Unlike the ocean, which feels global and interconnected, Baikal feels enclosed, self-contained, like a sealed archive, and archives can hold surprises. One of the most puzzling inhabitants of Lake Baikal is the Nerpa, a freshwater seal. Seals are marine mammals. They belong in oceans. Yet here, in the middle of Siberia, far from any sea, lives a thriving population of seals that have adapted entirely to freshwater conditions. How did they arrive? The prevailing theory suggests ancestors migrated through river systems during a distant glacial period, but the precise pathway remains debated. Genetic studies help reconstruct timelines, yet there are still gaps. The presence of a seal species in an isolated inland lake underscores how unusual Baikal's history must be. Every layer of sediment at the bottom contains microscopic fossils and chemical traces that record climate patterns stretching back millions of years. Ice ages, warm periods, shifts in vegetation. Even volcanic eruptions can leave detectable signatures. Drilling into those sediments is like drilling into time, but drilling is delicate work. Too much disturbance can alter the very record researchers seek to preserve. There is always tension between learning more and preserving what exists. Lake Baikal also experiences frequent earthquakes, not catastrophic ones most of the time, but enough to remind geologists that the rift is active. The ground beneath the lake is not stable bedrock in the comforting sense. It is moving, slowly but persistently. There have been moments in recorded history when sections of shoreline have shifted dramatically. Entire areas have sunk. The lake does not simply sit passively in its basin. It is part of an ongoing geological process. That ongoing process is one reason scientists approach Baikal with a mixture of fascination and caution. It is not just a lake to be measured, it is a dynamic system in mid-formation, and yet from above it can look serene. In summer, sunlight scatters across its surface in gentle ripples. Boats move across it without sensing the depth below. Small villages dot the coastline, forested slopes descend to pebbled beaches. It can appear peaceful enough to invite swimming. The surface does not advertise the complexity beneath. There is also methane. Recent studies have identified methane hydrates within Baikal's sediments. Methane trapped in ice-like structures under pressure. If destabilized, methane can escape into the water and potentially the atmosphere. In oceans, methane release events are studied carefully due to their climate implications. In Baikal, the scale is smaller, but the presence remains significant. Underwater plumes have been observed, bubbles rising through cold water. Most are small and gradual. Still, they signal chemical processes at work deep below. Scientists do not fear Baikal in the cinematic sense. They do not expect monsters to rise from it. Their concern is quieter. It is the realization that Baikal is both ancient and unfinished. Ancient systems can be resilient, but they can also be finely tuned. A change in temperature of a few degrees can shift oxygen levels in deep water. Altered inflow from rivers can disrupt nutrient balance. Invasive species, introduced accidentally, could outcompete endemic organisms that evolved without such competition. Because Baikal has been isolated for so long, many of its species have narrow tolerances. They are specialists, not generalists. That specialization is beautiful from an evolutionary perspective. It is also a vulnerability. And so, researchers continue to monitor, to measure, to lower sensors into cold depths, to analyze sediment cores, to map underwater ridges and hydrothermal vents. Each new discovery answers one question and often raises another. Standing at its shore, you might not feel threatened. You might simply feel small. Perhaps that is part of the Unease, a body of water that contains roughly 20% of the world's unfrozen freshwater, a basin that predates human civilization by tens of millions of years, a rift that is still widening, still reshaping the crust beneath. It reminds us that Earth is not static. It is easy to think of continents as fixed, of lakes as features that appear and remain. Baikal quietly contradicts that assumption. It demonstrates that land can tear, basins can deepen, and entirely new oceans can begin as narrow freshwater lakes. And that process is happening in slow motion, right now. When scientists describe Baikal, their voices often carry a note of respect. Not fear of immediate catastrophe, but respect for complexity, respect for age, respect for systems that operate on timescales far beyond a human lifespan. It forces perspective. We measure decades. Baikal measures millions of years. We think in terms of daily weather. Baikal archives entire climate eras in its mud. And as we continue to study it, to learn from it, to rely on its freshwater reserves, we're also altering the conditions that allowed it to remain stable for so long. That tension sits quietly beneath every research expedition. The water appears calm, the ice forms clean, geometric cracks in winter. Tourists photograph sunsets over mirrored surfaces. But below, the crust is shifting, sediment is settling, methane is seeping, species are adapting or struggling. Hydrothermal vents pulse gently in darkness, and scientists, equipped with instruments and data models, keep returning, drawn by questions that refuse to fully settle. Because Lake Baikal is not frightening in the way storms are frightening. It is unsettling in the way unfinished stories are unsettling. And that is where our exploration continues, moving deeper into its history and into the processes that shaped it, long before anyone stood on its shore and wondered what lay beneath the surface. When geologists first began to calculate the age of Lake Baikal, many of them assumed there had to be a mistake. Lakes, in geological terms, are usually temporary. They form, they fill with sediment, they dry up, they shift, or they freeze and vanish under glacial advance. Most lakes on Earth are less than 20,000 years old, leftovers from the last ice age. A few push into the hundreds of thousands. Some rare ones stretch to a couple of million years if conditions are unusually stable. Baikal does not follow that pattern. The current scientific estimate places its age at around 25 to 30 million years. That number alone changes how you look at it. 25 million years ago, the world was a different place. The Himalayas were still rising, grasslands were spreading across continents, the ancestors of modern elephants were smaller and stranger. Entire ecosystems have appeared and vanished since Baikal first began to open. And that is the first unsettling fact. This lake did not simply form in a depression and remain. It began as a crack. Beneath southern Siberia, the Earth's crust started to pull apart. Not violently, not with explosive drama. Slowly, relentlessly. The Baikal Rift Zone is one of the few places on land where continental crust is actively stretching. It is not yet an ocean, but it behaves like one in its early stages. Tectonic plates are separating by a few millimeters each year. That might not sound like much, but across millions of years those millimeters accumulate into kilometers. When the crust stretches, it thins. When it thins, it sinks. That sinking forms a basin. Over time, water collects. Most rift valleys either stop evolving or eventually flood with seawater, becoming new oceans. Baikal is still in the in-between stage. It is what geologists call a young ocean basin that never quite completed the transition. Except young here means tens of millions of years. The depth of the water is only part of the story. Beneath the water lies sediment that has been accumulating since the lake's earliest days. That sediment, compressed and layered, reaches more than 7 kilometers thick in some areas. If you were to drain the lake entirely and remove all the sediment, the full rift would be far deeper than the water alone suggests. In that sediment is a nearly continuous record of environmental history stretching back to the Oligocene epoch. Most lakes cannot preserve such a long archive. They fill too quickly. Rivers bring silt and organic material that gradually reduce depth. In many lakes, sediment builds up faster than the basin subsides. Eventually they become marshes, then plains. Baikal avoids that fate because it is still sinking. The crust continues to pull apart, allowing the basin to deepen as sediment accumulates. It is a balance between filling and stretching, a kind of geological tug-of-war that has allowed the lake to persist far longer than most freshwater bodies ever could. When researchers extract sediment cores from the bottom, they retrieve cylindrical samples that resemble stacked layers of dark and light bands. Each band corresponds to seasonal changes, volcanic ash, shifts in climate, microscopic organisms blooming and fading. It is an archive written in mud. Some of these cores extend back millions of years without interruption. That continuity is rare and precious in climate science. Ocean sediments can provide long records, but freshwater systems are often more fragmented. Baikal's record is unusually intact. It tells stories of warming and cooling cycles, of glacial advances that never quite erased it, of regional shifts in vegetation and rainfall. Through those layers, scientists reconstruct ancient temperatures, atmospheric composition, even patterns of wind. And through all those changes, the basin remained. That persistence raises questions. Why here? Why did this rift continue evolving while others stalled? Why did glaciers during the ice ages not scour it clean? Much of Siberia was covered in ice at various points, yet Baikal retained its depth and many of its endemic species. One explanation lies in its sheer size and depth. Glaciers can carve shallow lakes easily. But a basin more than a mile deep resists complete filling or removal. Even if ice covered the surface, the underlying depression remained vast. Another factor is geography. Baikal sits in a relatively dry continental interior compared to regions that experienced thicker glaciation. Ice sheets were present, but not always thick enough to erase the basin. Over millions of years, mountains rose around it. The Baikal Mountains and the Barguzin Range frame the lake today. Some of those peaks are geologically younger than the lake itself. That reversal feels counterintuitive. We often imagine mountains as ancient and lakes as recent. Here, the water predates parts of the surrounding landscape. When those mountains were lower, Baikal was already collecting sediment. When early primates were evolving in distant forests, Baikal was already deep. When the first hominins began walking upright in Africa, Baikal had been in existence for over 20 million years. That scale is difficult to hold in the mind. A lake that existed before humans, before humanity's ancestors, before many modern mammal lineages diversified. Its isolation during those spans of time allowed evolution to proceed in unusual directions. Species entering the lake early encountered little competition. Over time, they adapted to niches unique to this environment. Some fish evolved to survive near freezing water at great depths. Certain crustaceans developed filtering abilities that contribute to the lake's remarkable clarity. Because the lake persisted for so long without drying or drastically shrinking, those evolutionary pathways were not interrupted. In younger lakes, species often come and go as conditions fluctuate. In Baikal, continuity allowed specialization, and specialization can produce strangeness. There are more than 2,500 known species in Lake Baikal. Over half are endemic, found nowhere else. That level of endemism is extraordinary for a freshwater system. It rivals isolated oceanic islands in evolutionary uniqueness. It also means the lake is less replaceable. If Baikal were to change rapidly, many of those species would have nowhere else to go. When scientists speak of Baikal's age, they do not mean simply that water has been sitting there for millions of years. Water molecules cycle in and out through rivers and evaporation. The age refers to the basin itself, the tectonic depression that has continuously held water through geological upheavals. That depression is not static. Seismic studies reveal faults beneath the lake that are still active. Earthquakes occur regularly in the region. Most are moderate, rarely catastrophic, but they confirm that the rift is alive. The land continues to stretch. In some areas, hydrothermal vents release warm water and minerals from deep below. These vents were discovered relatively recently, surprising researchers who did not expect such ocean-like features in a freshwater lake. Hydrothermal systems require heat. Heat implies tectonic activity. Activity implies change. All of this means Baikal is not merely old, it is old and still evolving. Geologists sometimes describe Earth's surface as a dynamic skin, constantly recycled through plate tectonics. Oceans open and close over hundreds of millions of years. Continents collide and separate. In that grand cycle, Baikal represents an early stage in ocean formation that has been paused but not stopped. If continental rifting continues for tens of millions more years, the basin could widen enough to allow seawater intrusion. At that point, Baikal would cease to be a freshwater lake and begin transforming into an inland sea. That possibility is distant, measured in geological time rather than human history. Still, the process has begun. The crust beneath the lake is thinner than surrounding regions. Magnetic and gravity surveys confirm the structural differences. When you stand at its edge, you're standing beside a continental seam. Most of us do not think of lakes as seams. We think of them as features within stable land. Baikal challenges that assumption. It is the visible expression of a fracture that extends deep into the mantle. Researchers have drilled into the sediment to understand how the basin formed. By analysing microfossils and chemical signatures, they piece together the timeline of subsidence. They can identify periods when the lake deepened more rapidly, possibly linked to pulses of tectonic extension. Those pulses may correlate with broader plate movements affecting Asia. The collision between the Indian subcontinent and Eurasia, which raised the Himalayas, altered stress patterns across vast regions. Some scientists suspect that distant tectonic forces influenced the evolution of the Baikal Rift. In that sense, Baikal is connected to mountain building thousands of kilometers away. Its age reflects not just local processes but continental scale dynamics. Climate history adds another layer. Because the sediment record is so long, Baikal provides insight into how continental interiors responded to global shifts. During warmer epochs, surrounding vegetation changed. During colder periods, dust deposition altered sediment composition. Even volcanic eruptions from distant regions left thin ash layers that can be identified and dated. Each layer confirms continuity. There are very few freshwater systems on Earth with such an unbroken record. That continuity allows scientists to test climate models. If models predict certain temperature shifts during a known epoch, sediment data from Baikal can confirm or challenge those predictions. The lake functions as both subject and archive, but its age also means it has experienced fluctuations beyond what we consider normal. Over millions of years, water levels have risen and fallen, shorelines have shifted, river inflows have altered, yet the basin endured. Endurance, however, does not equal invulnerability. Conditions today are changing at a pace that may exceed natural variability recorded in its sediments. Industrial development near certain areas has introduced pollutants. Warming trends influence ice cover duration. Reduced ice thickness affects ecosystems that rely on seasonal cycles. Because Baikal evolved under relatively stable long-term conditions, rapid change could be disruptive. Its age magnifies the stakes. If a lake formed 10,000 years ago changes, that is one thing. If a system that has persisted for 30 million years begins to destabilize within a few centuries, that shift is stark. Scientists are cautious in their language. They avoid dramatization. Yet there is a quiet awareness that Baikal's longevity does not guarantee future stability. It has survived tectonic stretching, glacial periods and climatic oscillations. It may face different challenges now. The mountains around it continue to rise gradually due to tectonic forces. Erosion feeds sediment into the basin. Earthquakes reshape parts of the shoreline. These are slow processes, but they remind researchers that the landscape is not fixed. When early explorers first encountered Lake Baikal, they could not have known its age. They saw vast water and perhaps sensed its scale. Modern science reveals the deeper timeline, 25 to 30 million years, older than many mountain ranges, older than the Mediterranean Sea in its current form, older than the African Great Lakes, which themselves are ancient by most standards. That age does not make Baikal aggressive or hostile, it makes it patient. And patience in geology means processes unfolding over spans that dwarf human comprehension. The sediment continues to settle at the bottom, millimetre by millimetre. The crust continues to pull apart. Hydrothermal systems continue to circulate heat from below. Species continue to evolve in relative isolation. Nothing about it is static. When researchers map the lake floor using sonar, they find steep slopes, underwater ridges, fault scarps. The basin is not a simple bowl. It is segmented into subbasins separated by structural highs. Each subbasin may have slightly different sediment thickness, heat flow and biological communities. The complexity matches its age. A young lake might have smooth contours carved by recent glaciation. Baikal's structure reflects millions of years of tectonic interplay. Standing beside it today, you see surface waves and perhaps a line of mountains. Beneath that view lies a depression that has been forming since before many modern ecosystems existed. It is an unusual experience to consider that the water before you has occupied that location since long before mammals resembled what they do now, and the story of its depth, which grows from that age, leads naturally into the next layer of understanding, because age alone does not unsettle scientists as much as what that age has allowed to accumulate beneath the surface. When people hear that Lake Baikal is the deepest lake on Earth, they often imagine a number and then move on. 1,642 metres. It sounds impressive. It sounds dramatic. But numbers alone do not always translate into understanding. Depth, especially that kind of depth, is difficult to visualize unless you slow down and compare it to something familiar. If you were to stand the Empire State Building upright at the bottom of Baikal, there would still be hundreds of meters of water above its antenna. If you dropped the Eiffel Tower into the lake, it would vanish completely beneath the surface with room to spare. Even the tallest skyscrapers would disappear as if lowered into an endless shaft. And that is just the water. What unsettles scientists is not only that Baikal is the deepest lake on Earth, but that it behaves in ways more typical of an ocean basin than a freshwater body. Its depth alters pressure, temperature, circulation, chemistry, and biology in ways that are unusual for inland water. Pressure increases by about 1 atmosphere for every 10 meters of depth. At the bottom of Lake Baikal, the pressure exceeds 160 atmospheres. That means every square centimetre down there supports a force more than 160 times what you experience at the surface. For comparison, that is similar to the pressure at some mid-ocean depths. In most lakes, depth is measured in tens of metres, maybe a few hundred. Pressure is noticeable but not extreme. In Baikal, the lower layers exist under conditions that reshape matter and life. The temperature at the bottom hovers just above freezing year-round, around 3 to 4 degrees Celsius. Light does not penetrate anywhere near that far. Sunlight fades within the upper layers, and below a few hundred meters the water becomes permanently dark. Darkness and cold are common in the deep ocean, but rare in freshwater systems of this scale. This creates vertical zones within the lake. The upper layers respond to seasonal changes. In summer, sunlight warms the surface. In winter, ice forms, sometimes thick enough to support vehicles. Beneath that seasonal skin lies a more stable world. One might assume that such depth leads to stagnation, that deep water would sit motionless for centuries. In many deep lakes, bottom waters become depleted of oxygen over time because mixing is limited. Oxygen consumed by decomposing material is not easily replenished. Baikal defies that expectation. Studies have shown that its deep waters remain oxygenated. That is extraordinary. It suggests active circulation mechanisms transporting oxygen downward. Scientists believe that seasonal cooling and wind-driven mixing combined with the lake's elongated shape and complex underwater topography help drive vertical currents. In winter, when surface water cools and becomes denser, it can sink, carrying oxygen with it. This allows life to persist even at extreme depths. Still, reaching those depths is not simple. Submersibles have been deployed to explore Baikal's bottom. In the 2000s, Russian research submersibles descended to the deepest points. The descent takes time. The water darkens gradually. Light from the surface fades into a dim green, then grey, then black. Down there, the lake floor appears uneven. Slopes descend sharply. Sediment blankets some areas, while others reveal rocky outcrops and signs of faulting. Hydrothermal vents release warmer water from beneath the crust, forming plumes that rise slowly. It does not look like a typical lake bottom. Because of its rift origin, Baikal is segmented into 3 main basins: the southern, central, and northern basins. Each has its own maximum depth. The central basin reaches the deepest measured point. Between basins, underwater ridges act like submerged mountain ranges. These structural divisions influence circulation and sediment deposition. They also create distinct ecological niches. Depth changes everything. At shallower depths, organisms rely on photosynthesis and nutrient cycles driven by sunlight. Phytoplankton bloom during certain seasons, supporting zooplankton and fish. Near the surface, familiar freshwater processes operate. But below several hundred meters, photosynthesis is impossible. Life must rely on other energy sources. Organic matter sinking from above provides some nutrients. Hydrothermal activity may contribute minerals. Certain microorganisms metabolize chemicals in ways that do not depend on light. In Baikal's deepest zones, researchers have discovered unique amphipods, crustaceans adapted to high pressure and low temperature. Some are nearly transparent, others have elongated limbs suited for navigating soft sediment. These organisms evolved in isolation under stable, extreme conditions. They are not relics from oceans, but freshwater species that adapted to ocean-like pressures. That combination is rare. Most deep-sea organisms have marine ancestry. Deep lake organisms in Baikal evolved from freshwater ancestors that gradually colonized deeper habitats as the basin subsided over millions of years. As the lake deepened, species either adapted or remained in shallower regions. Over geological time, natural selection favoured traits that allowed survival under crushing pressure and cold darkness. The result is a layered ecosystem, vertically structured like a hidden tower of life. Scientists are cautious when exploring these zones. Disturbance can damage fragile communities. Sampling requires specialised equipment that can withstand pressure while preserving organisms intact. One unexpected feature of Baikal's depth is its clarity even at significant distances below the surface. The lake is famous for its transparency, sometimes reaching 40 metres in visibility. That clarity results largely from tiny crustaceans called Episcora baikalensis, which filter microscopic particles continuously. Their efficiency removes suspended material that would otherwise cloud the water. In effect, the lake cleans itself. However, clarity at the surface does not mean clarity at depth. Fine sediment still settles slowly over time. When submersibles disturb the bottom, clouds of silt can obscure vision instantly. That sediment is part of the deeper story. More than 7 kilometers of accumulated sediment lie beneath the water. That thickness is extraordinary for a freshwater basin. Ocean basins accumulate sediment over vast spans, but inland lakes rarely reach such depths. The combined depth of water and sediment means that the crust beneath Baikal is thinned dramatically compared to surrounding regions. Seismic imaging reveals that the lithosphere beneath the rift is stretched and weakened. This thinning contributes to heat flow. Measurements indicate elevated geothermal gradients in parts of the lake. That heat supports hydrothermal systems similar in some ways to those found along mid-ocean ridges. Hydrothermal vents in Baikal are not as spectacular as black smokers in the ocean, but they are significant. Warm water rising from beneath carries dissolved minerals, influencing local chemistry. In winter, some of this activity manifests in curious ways at the surface. Large circular patterns sometimes appear in the ice, visible from satellites. These rings, spanning several kilometers, are linked to warm water currents beneath the ice. Where warmer water rises, ice may thin or melt differently, forming circular structures. At first glance, such rings can look mysterious. In reality, they are physical expressions of deep circulation, driven by temperature differences and possibly geothermal inputs. Even so, they are reminders that depth communicates with the surface. Another feature of extreme depth is methane. Within the sediments, methane hydrates form under pressure and low temperature. These ice-like structures trap methane molecules in crystalline cages of water. Methane hydrates are common in deep ocean sediments, but their presence in Baikal underscores how ocean-like its conditions can be. If destabilized, methane hydrates can release gas bubbles upward. Researchers have observed plumes rising through the water column. Most are small and gradual, but they indicate chemical processes active far below. Methane release also raises questions about climate interactions. Although Baikal's contribution to global methane budgets is small compared to oceans and wetlands, understanding these processes helps scientists model similar systems elsewhere. Depth also affects sound. In large bodies of water, temperature and pressure gradients create layers that bend sound waves. In Baikal, acoustic studies reveal complex propagation patterns. Sound can travel long distances under certain conditions, reflecting off layers of varying density. This matters for research. Sonar mapping relies on understanding how sound behaves in deep water. The complex topography and stratification of Baikal require careful calibration. For humans, depth introduces risk. Diving beyond recreational limits requires specialized gear. The cold temperatures pose additional hazards. Hypothermia is a constant threat. Even small errors in pressure management can be dangerous. That risk is one reason much of Baikal's deepest regions remain sparsely explored compared to coastal areas. There is also a psychological component. Descending into a freshwater body more than a mile deep, knowing that beneath you lies sediment recording tens of millions of years, can feel disorienting. Unlike the open ocean, where vastness extends horizontally as well as vertically, Baikal's depth exists within a narrow enclosed basin. You're surrounded by land, yet below you is an abyss. That contrast unsettles some researchers. It challenges intuitive expectations about lakes, and the lake continues to deepen. Geological measurements indicate that the rift widens by a few millimeters each year. That widening contributes to subsidence. Over millions of years, the basin may grow deeper still. The interplay between sediment accumulation and tectonic stretching determines net depth changes. If stretching outpaces sediment filling, maximum water depth could increase. In practical human terms, changes are too slow to notice. In geological terms, they are significant. The depth also influences weather patterns locally. Large volumes of water store heat differently than surrounding land. Baikal moderates temperatures in nearby areas. In winter, the massive body of water releases stored heat slowly, affecting microclimates along the shore. In summer, it absorbs heat, stabilizing air temperatures. Yet despite its moderating effect, the lake itself is sensitive to climate change. Ice cover duration has shortened in recent decades. Ice thickness varies more than historical averages suggest. Depth buffers temperature changes somewhat. Deep water remains cold even during warmer years, but surface layers respond quickly to atmospheric shifts. That vertical contrast can alter mixing patterns. If surface water warms earlier in the year, density gradients strengthen, potentially reducing vertical circulation. Reduced mixing could limit oxygen transport to deeper layers. Scientists monitor such trends carefully. Oxygenated deep water is crucial for maintaining the unique benthic communities that evolved there. The deeper the lake, the more inertia it has. Large systems resist rapid change. But when change does occur, effects can propagate through layers in complex ways. Baikal's depth also influences its symbolic status. Deepest lake, largest freshwater volume, oldest continuous freshwater basin. These labels draw attention, but they also emphasize responsibility. A system that extreme holds disproportionate ecological and scientific value. Researchers from around the world collaborate on Baikal studies. Sediment cores are analysed in laboratories thousands of kilometres away. Genetic sequencing reveals evolutionary histories hidden in microscopic organisms. Each new expedition uncovers details that refine understanding of how such depth functions within a continental rift. And still, much remains unknown. Some deep zones have been visited only a handful of times. Certain microbial communities are barely characterised. The full extent of hydrothermal activity is not completely mapped. Depth hides. It hides data. It hides species. It hides geological structures. That concealment is not malicious. It is simply a function of scale and pressure and darkness. But it contributes to the quiet tension scientists feel when discussing Baikal. The knowledge that beneath an apparently tranquil surface lies one of the deepest freshwater environments on Earth, shaped by forces that are ongoing and not entirely predictable. From the shore, you see horizon and reflection. From the bottom, if you could stand there, you would see sediment stretching back millions of years, pressure pressing from all sides, and faint currents moving through near-freezing water. And the depth is not an isolated fact. It is a consequence of age and tectonic motion, and it sets the stage for everything that lives within the lake and everything that might change in the future. Because once you understand how deep it truly is, the next question arises naturally. What kind of forces are still at work down there, continuing to shape the basin even now? If you look at a map of Asia and trace your finger across southern Siberia, Lake Baikal appears as a long, narrow shape, almost like a blade laid gently across the landscape. It does not sprawl outward like the Great Lakes of North America. It does not spread in wide circular basins. It stretches. That shape is not accidental. Lake Baikal exists because the earth beneath it is being pulled apart, very slowly, not with the violence of an earthquake tearing a city in seconds, but with a persistent tension that has been active for tens of millions of years. The Baikal Rift Zone is one of the few places on land where continental crust is actively extending. The ground on either side of the lake is moving away from each other by a few millimeters every year. Millimeters sound harmless. Over a human lifetime, that separation would be difficult to measure without instruments. Over 1,000,000 years, it becomes kilometers. To understand why this matters, it helps to step back and consider how continents behave. The outer shell of the Earth is divided into tectonic plates. These plates move, driven by heat deep within the planet. Sometimes they collide, raising mountains like the Himalayas. Sometimes they slide past each other, as along the San Andreas Fault, and sometimes they pull apart. When plates pull apart beneath oceans, new seafloor forms. Magma rises, cools, and creates fresh crust. That process built the Atlantic Ocean. Once, Africa and South America were joined. Over millions of years they drifted apart and an ocean opened between them. On land, when continental crust begins to stretch, it forms what geologists call a rift valley. The crust thins, faults develop, blocks of land drop downward, forming elongated basins. Lake Baikal occupies one of those basins. What makes it unsettling for scientists is not that it formed from rifting, but that the rifting has not stopped. Seismic measurements confirm ongoing activity. Earthquakes occur regularly in the region. Most are moderate, but they are clear evidence that stress continues to accumulate and release along faults beneath and around the lake. The rift extends for more than 2,000 kilometers. Baikal is its most visible and dramatic expression, but the entire zone represents a structural weakness in the continent. Geologists studying the area use GPS instruments capable of detecting movements of just a few millimeters per year. Those instruments show that the crust is still widening. The two sides of the lake are slowly separating. When crust stretches, it does not do so evenly. Large fault blocks tilt and drop. Some sections sink more than others. That is why Baikal is divided into distinct sub-basins with varying depths. The central basin is the deepest. The southern and northern basins are slightly shallower, separated by underwater ridges formed by structural highs. These ridges are not random. They are remnants of crustal blocks that did not sink as much as surrounding areas. If you were to slice the earth vertically through Lake Baikal, you would see a cross-section resembling a stretched and fractured layer cake. The crust beneath the lake is thinner than surrounding regions. Beneath that thinned crust, heat from the mantle rises more easily. Heat weakens rock. Weak rock deforms more readily. This feedback loop allows the rift to persist. One question that has puzzled scientists for decades is why the Baikal Rift exists where it does. Continental interiors are typically more stable than plate boundaries near oceans. Yet here, far from coastal spreading centres, the land is pulling apart. Several theories attempt to explain this. One points to far-field stresses from the collision between the Indian plate and the Eurasian plate. When India rammed into Asia, it raised the Himalayas and deformed crust across vast distances. That collision may have redistributed stress within the Eurasian plate, contributing to extension in regions like Baikal. Another theory involves mantle plumes or upwellings of hot material rising from deep within the earth. Elevated heat flow beneath Baikal suggests thermal anomalies. If hot mantle material weakens the crust from below, it can promote rifting. The exact combination of forces is still debated. What is not debated is that the rift is active. In 1862, a dramatic reminder occurred. An earthquake caused part of the Selenga River delta to collapse, forming a new bay known as Proval Bay. Land subsided suddenly, flooding previously dry ground. It was a localized event, but it demonstrated how dynamic the region can be. Such events are rare, yet they underscore the fact that Baikal is not a passive lake resting in ancient bedrock. It sits atop a fracture system that continues to evolve. The presence of hydrothermal vents in the lake further confirms ongoing tectonic and geothermal activity. Warm water enriched with minerals seeps upward through cracks in the lakebed. These vents are smaller and less visually dramatic than those in deep oceans, but they indicate heat flow from beneath. Hydrothermal systems can influence local chemistry, creating microhabitats for specialized microorganisms. In some areas, researchers have detected unusual concentrations of dissolved gases and minerals associated with vent activity. These features are not typical of most freshwater lakes. When continents split and oceans form, there is usually a transitional stage. The East African Rift provides a modern example. There, large lakes like Tanganyika and Malawi occupy rift valleys that may one day widen into new ocean basins. Lake Tanganyika is often compared to Baikal because it is also deep and ancient. Yet Baikal surpasses it in both age and depth. Geologists sometimes describe Baikal as a prototype for early ocean formation that has stalled mid-process. The question that lingers is whether it will remain stalled. If rifting continues uninterrupted for tens of millions of years, seawater could eventually flood the basin. That would transform Baikal from a freshwater lake into a marine environment. That transformation would not happen suddenly. It would require continued crustal thinning, further widening, and connection to an ocean basin. It is a distant possibility on a geological timescale, but the process that could lead there is happening now. The sense of unease among scientists does not come from immediate catastrophe. It comes from awareness of slow inevitability. Continents are not eternal in their current shapes. Where there is tension in the crust, change accumulates. Seismic surveys beneath Baikal reveal faults cutting deep into the crust. Some faults extend down to the mantle. Earthquakes cluster along these structures. The distribution of seismic activity helps scientists map where stress is concentrated. Patterns show that the rift is not uniform. Some segments are more active than others. The central basin, being the deepest, reflects significant subsidence. That subsidence corresponds to greater stretching in that segment. In addition to earthquakes, geologists study gravity anomalies in the region. Variations in gravity can indicate differences in crustal thickness and density. Measurements show reduced density beneath the rift, consistent with thinned crust and possible mantle upwelling. Magnetic surveys add another layer of information. As magma intrudes into cracks and cools, it can alter magnetic signatures. Evidence suggests that magmatic activity has occurred beneath Baikal in the past, though large-scale volcanic eruptions are not common at the surface. Still, the presence of volcanic rocks in surrounding regions hints at a more active geological past. Over millions of years, rift systems can experience pulses of activity. Periods of relative calm may alternate with phases of accelerated extension. Sediment cores from Baikal sometimes record changes in deposition rates that may correlate with tectonic pulses. Increased erosion during uplift events can alter sediment composition. The lake, in this sense, records its own tectonic history. From the shoreline, you would not necessarily sense that the ground beneath your feet is part of an active rift system. The landscape can appear stable, forested and quiet, yet instruments reveal constant motion. GPS stations anchored in bedrock transmit tiny positional shifts over time. These shifts confirm that the two sides of the lake are gradually drifting apart. When scientists overlay those measurements on geological maps, the pattern becomes clear. Baikal is the visible surface expression of a continent in tension. That tension also influences the surrounding mountains. As crust stretches in the centre, adjacent blocks can tilt upward. This contributes to uplift in ranges bordering the lake. In some places, steep cliffs drop directly into the water, marking fault lines where blocks have moved relative to one another. The shape of the shoreline often reflects underlying structure. Straight segments may trace fault boundaries. Sudden depth increases near shore indicate steep fault scarps continuing underwater. Bathymetric maps reveal dramatic slopes beneath the surface. In some areas, the lake floor drops sharply within a short horizontal distance from shore. This is not typical of lakes formed solely by glacial carving. It is characteristic of tectonic basins. The idea that Baikal may one day become an ocean changes how scientists frame its study. It is not merely an ecological treasure, it is a geological process in progress. Comparisons with the Red Sea are instructive. The Red Sea began as a rift valley between Africa and the Arabian Peninsula. Over time, it widened and filled with seawater, becoming a narrow ocean basin. Baikal is earlier in that sequence. The difference is that Baikal is entirely continental and far from any present ocean connection. For seawater to reach it, dramatic changes in global geography would need to occur. That is not expected anytime soon. Yet even without ocean invasion, continued rifting could deepen and widen the basin further. One might ask whether rifting could accelerate. Geological history shows that extension rates can vary. However, current measurements suggest relatively steady movement. Earthquakes in the region remind residents and scientists alike that the crust is not at rest. In 1959, a magnitude 6.8 earthquake struck near Baikal. Other moderate events have occurred since. These earthquakes do not usually cause widespread devastation due to the relatively low population density around the lake, but they confirm that stress accumulates and releases. Underwater landslides triggered by seismic activity can disturb sediments. Such disturbances can create turbid currents that redistribute material across the basin floor. Each earthquake subtly reshapes the underwater landscape. Hydrothermal activity is also influenced by tectonic motion. Faults provide pathways for heated fluids to rise. Where those fluids emerge, they alter local ecosystems. Scientists using remotely operated vehicles have documented vent fields at depths of more than 1,300 meters. Around some vents, microbial mats form, supported by chemical energy rather than sunlight. These discoveries blur the line between freshwater and marine environments. The deeper researchers look, the more Baikal resembles an embryonic ocean, rather than a simple lake. That resemblance contributes to the quiet tension in scientific discussions. A lake implies containment. A rift implies separation. Separation implies transformation. It is not a matter of fear in the cinematic sense. It is a recognition that the land beneath Baikal is not finished shaping itself. If you imagine placing your hand flat against the ground near the lake, it would feel solid, stable. Yet beneath that surface, rock is bending and fracturing under immense forces generated deep within the earth. Those forces are indifferent to human timelines. They operate on scales measured in millions of years. From a human perspective, Baikal will likely remain a lake for countless generations. From a geological perspective, it is partway through a process that may eventually redraw maps. The water above reflects clouds and sky. Below, the crust stretches, and as scientists continue mapping faults, measuring heat flow, and tracking seismic tremors, they are not just studying a lake. They're observing a continent slowly pulling itself apart 1 millimeter at a time, shaping the deepest freshwater basin on Earth, and setting conditions for everything that lives within it. If you stand on the rocky shoreline of Lake Baikal on a calm day and look down into the water, the first thing you notice is not the depth. It is the clarity. Rocks several meters below the surface appear sharply defined. Pebbles seem close enough to reach. In certain seasons, visibility can extend 40 meters or more. That is not a casual exaggeration. It is a measurement confirmed repeatedly by divers and researchers. 40 meters. In a body of fresh water that contains roughly 1/5 of the world's unfrozen freshwater supply. Most large lakes do not look like this. Large lakes tend to be stirred by wind, fed by rivers carrying sediment, influenced by algae blooms, and clouded by suspended particles. Even lakes considered clean usually have a faint haze to their water, especially in deeper areas. Baikal often looks like polished glass. Scientists have spent decades studying why. The answer is not magic, it is biological. At the centre of this clarity is a tiny crustacean called a Piscura baicalensis. It is a copepod, barely visible to the naked eye, yet present in extraordinary numbers. In some estimates, these organisms make up a significant portion of the lake's zooplankton biomass. Their role is simple and relentless. They filter. Episcura feeds on microscopic algae and organic particles suspended in the water. Every day, billions upon billions of these tiny organisms pass water through their bodies, removing material that would otherwise remain floating. They are in effect living filtration units. Most lakes have zooplankton. Few rely so heavily on a single endemic species to maintain such large-scale transparency. Episcura evolved in Baikal over millions of years. The lake's isolation allowed this species to specialize. It thrives in cold water, tolerates seasonal changes, and maintains populations even in deeper zones. The result of this constant filtration is water that appears almost unnaturally pure. But clarity alone does not tell the whole story. Baikal's water is also low in dissolved minerals compared to many other large lakes. Rivers feeding the lake pass through relatively unindustrialized regions. Historically, human influence along the shoreline was limited compared to more densely populated areas around other freshwater systems. Low nutrient input reduces the likelihood of excessive algae blooms. In many lakes worldwide, nutrient pollution from agriculture and urban runoff leads to eutrophication. Algae multiply rapidly, turning water green and opaque. When algae die and decompose, oxygen levels drop, harming fish and invertebrates. Baikal has largely avoided large-scale eutrophication, though not entirely without warning signs. Its clarity is partly a product of geological youth relative to some basins, and partly a result of long-term ecological balance. However, what unsettles scientists is not simply that the water is clear, but how delicate that clarity may be, because systems that appear pristine can sometimes be the most vulnerable. The filtration performed by Episcura is temperature dependent. These organisms function best within a certain range. If surface waters warm significantly due to climate change, their life cycles could shift. Even small changes in temperature can alter reproduction rates, seasonal timing, and distribution patterns. If Episcura populations decline, suspended particles would accumulate more readily. Water that has been clear for millions of years could become cloudier within decades. Researchers have already observed subtle changes in some parts of the lake. In certain shallow bays near urbanized areas, filamentous algae have begun to grow more densely than historical records suggest. These blooms are linked to localized pollution and nutrient input. While these effects are currently limited in scale compared to global examples of freshwater degradation, they serve as reminders that clarity is not guaranteed. There is also the matter of microplastics. Studies conducted in recent years have detected microplastic particles in Baikal's water column. The concentrations are lower than in heavily polluted lakes, but their presence is undeniable. Microplastics can be ingested by zooplankton, including Episcura. If these particles interfere with feeding efficiency or reproduction, filtration capacity could decline. Scientists are investigating how resilient Baikal's filtration network truly is. Another component of clarity lies in vertical mixing. As mentioned earlier, Baikal's deep waters remain oxygenated due to seasonal circulation patterns. In winter, as surface water cools, it sinks, carrying oxygen downward. In spring and autumn, wind-driven mixing redistributes nutrients and oxygen. This mixing prevents the accumulation of stagnant layers that often trap sediments in other deep lakes. But mixing depends on temperature gradients. If surface warming intensifies and ice cover duration shortens, density differences between layers may strengthen, reducing vertical circulation. Reduced mixing could limit nutrient redistribution and alter plankton dynamics. Clarity, then, is tied to climate stability. In the early 20th century, ice covered Baikal for about 4 to 5 months each year. Recent observations show shorter ice seasons. Ice forms later and melts earlier. Ice influences light penetration and water temperature. Under ice, sunlight can still penetrate because Baikal's ice is remarkably transparent in many areas. This transparency supports winter phytoplankton activity. When ice duration changes, seasonal biological rhythms shift. Such shifts ripple through the ecosystem. Scientists are careful not to overstate changes, but long-term monitoring indicates that trends are measurable. One paradox of Baikal's clarity is that it allows researchers to see further into the water column during dives and submersible missions. This visibility aids mapping and biological surveys. Yet the same clarity also means that any decline becomes visually obvious. In many polluted lakes, opacity hides degradation. In Baikal, even subtle changes in transparency attract attention. The lake's clarity is also influenced by the absence of certain types of fish that stir up sediment. In shallower lakes, bottom-feeding fish can resuspend particles, reducing transparency. Baikal's deep zones are dominated by species adapted to cold, stable conditions, many of which do not disturb sediment in ways that cloud the water. The rocky shoreline in many regions also reduces sediment input compared to lakes bordered by soft soils. Still, rivers feeding Baikal carry silt, especially during spring snowmelt. The largest inflow, the Selenga River, contributes a substantial portion of the lake's water and sediment load. Despite this input, the lake's massive volume dilutes suspended material effectively. Volume matters. With roughly 23,600 cubic kilometers of water, Baikal's scale acts as a buffer. Particles introduced at one location disperse across enormous space. Yet buffering has limits. Localized pollution near industrial sites in the past, such as the Baikalsk pulp and paper mill, raised serious concerns. Effluent discharge introduced chemicals that threatened water quality. After years of debate and environmental activism, the mill was eventually closed. Remediation efforts continue. The episode demonstrated that even a lake of Baikal's size is not immune to concentrated industrial impact. Scientists studying clarity often measure what is known as Secchi depth, a simple yet effective method involving a black and white disc lowered into the water until it disappears from view. In Baikal, Secchi depths frequently exceed those recorded in most other large lakes. High Secchi depth values indicate low turbidity, but clarity does not mean sterility. Baikal supports complex food webs. Phytoplankton bloom seasonally, providing energy for zooplankton, which in turn feed fish and other organisms. Clarity reflects balance, not absence. There is something psychologically striking about looking into water so clear that it appears almost invisible. In many lakes, water is visibly present. In Baikal, it can feel as though rocks and depths are simply there, unmediated by liquid. Divers describe the experience as disorienting. When descending, there is less visual cue of water density than in murkier environments. The boundary between air and water feels sharper at the surface, but below the medium seems transparent enough to forget. This visual clarity contrasts with the physical reality of pressure and cold. At depth, despite the clear appearance, conditions are extreme. Scientists studying underwater habitats sometimes remark that Baikal feels more like diving into a vertical landscape than into water. Clear water enhances that sensation. The clarity also contributes to the lake's iconic winter appearance. When ice forms, it can be remarkably transparent. Bubbles trapped beneath the surface freeze in vertical columns. People walking across the ice report seeing meters down into the water. Photographs show intricate crack patterns and methane bubbles suspended in ice like strings of pearls. These images travel widely online, reinforcing Baikal's reputation as pristine and otherworldly. But methane bubbles also remind researchers of processes occurring below. Gas hydrates in sediment release methane gradually. In winter, as water near the surface freezes, rising bubbles can become trapped in ice layers. Most methane release dissolves or oxidizes before reaching the atmosphere. Still, monitoring continues. Clarity makes these bubbles visible. Without clear water and transparent ice, Such details would be harder to observe. There is also a chemical dimension to Baikal's purity. The lake's water has relatively low concentrations of dissolved salts compared to oceans. It is fresh water after all. But even among freshwater systems, its chemical composition is notable for stability. Long residence time contributes to this. Water entering Baikal remains there for an average of about 330 years before flowing out through the Angara River. That means water molecules cycle slowly compared to smaller lakes. Slow turnover can be a double-edged sword. On one hand, it allows stable chemical conditions to persist. On the other, it means contaminants introduced into the system can remain for centuries. Clear water, then, is not just a visual feature. It is an indicator of complex interplay between biology, chemistry, and geology. Scientists analysing sediment cores often note that clarity has varied over millions of years. Certain periods show increased organic deposition, suggesting stronger productivity or reduced filtration efficiency. Clarity is not constant across geological time, but the baseline over recent millennia has been remarkably high. This long-term consistency creates an expectation. When people visit Baikal and see through its waters to stones below, they assume that clarity is natural and permanent. Researchers know better. They understand that it is the product of evolved systems and stable conditions, and evolved systems can be disrupted. There is also a philosophical dimension to water that appears so pure. Clarity suggests transparency, honesty, simplicity. Yet beneath Baikal's clear surface lies one of the most geologically dynamic regions in continental Asia. The water looks calm and uncomplicated. The crust below stretches and fractures. The microorganisms filtering suspended particles operate without awareness of global climate shifts or industrial pressures. They simply perform their role. Scientists often speak of resilience, but resilience has thresholds. One of the challenges in studying Baikal is predicting where those thresholds lie. How much warming would significantly reduce Episkura populations? How much nutrient input would trigger persistent algal blooms? How would altered mixing patterns affect oxygen levels at depth? These questions remain open. Long-term monitoring programs track temperature profiles, plankton abundance, nutrient concentrations, and clarity metrics year after year. Trends are subtle but meaningful. Some studies suggest increasing surface water temperatures over recent decades. Others note changes in phytoplankton community composition. Change does not always mean collapse. But in a system that has remained stable for millions of years, even small deviations attract scrutiny. Because when water that should not be this clear begins to lose its transparency, it is not merely an aesthetic loss. It signals structural shifts within one of Earth's most ancient freshwater ecosystems. And clarity, once diminished, may not return easily. The filtration network that keeps Baikal so transparent is the product of millions of years of evolution within an isolated basin formed by tectonic forces still at work. Understanding that link between visible purity and hidden instability leads naturally toward the next layer of inquiry, where life that exists nowhere else depends on conditions that have persisted longer than most landscapes surrounding the lake. When scientists say that more than half of Lake Baikal's species exist nowhere else on Earth, it sounds like a statistic meant to impress. It is not meant to impress. It is meant to describe isolation. Isolation over millions of years produces outcomes that feel almost improbable when you line them up side by side. In Baikal, that isolation was not caused by an island surrounded by ocean, but by a freshwater basin surrounded by land and locked within a rift valley that remained stable for tens of millions of years. Most lakes are temporary in geological terms. Species enter them, adapt briefly, and then either migrate away, go extinct, or become part of larger connected systems. Baikal did not follow that path. Because the basin persisted and continued deepening, species that entered early found themselves in a contained world with little competition from outside. Over time, evolution began to experiment. Today, researchers have catalogued more than 2,500 species in the lake. Roughly 60% of them are endemic. That means they evolved there and live nowhere else. That proportion is extraordinary for freshwater. The first organisms scientists often mention are the amphipods. Amphipods are small crustaceans related distantly to shrimp. In most freshwater systems, amphipods are present but not especially diverse. In Baikal, there are more than 350 species of amphipods alone. 350. Some are only a few millimeters long. Others reach lengths of several centimeters. Some are nearly transparent, their internal organs faintly visible through pale bodies. Others are armoured, spiny, or coloured in muted shades of green or brown. They occupy nearly every depth of the lake, from shallow rocky shores to the deepest basins more than a kilometre below the surface. Over millions of years, as the lake deepened, amphipods adapted to increasing pressure and decreasing light. Species that once lived in shallower zones gradually colonised deeper habitats. Genetic studies suggest that many Baikal amphipods share common ancestors that entered the lake long ago. Subsequent isolation within different subbasins and depth zones led to diversification. It is adaptive radiation, similar in principle to Darwin's finches on the Galapagos Islands, but occurring underwater in a continental rift. Because the lake remained relatively stable, these evolutionary branches were not cut short by drying or drastic habitat loss. The result is a vertical ecosystem layered by depth. At shallow levels, amphipods graze on algae and organic debris. In deeper zones, others scavenge on sinking detritus. Some species have elongated appendages for walking across soft sediment. Others cling to rocks near hydrothermal vents. Hydrothermal vents in freshwater are rare enough. Species that evolve to exploit such vents in a lake are rarer still. Researchers have documented amphipods congregating around vent areas where mineral-rich water rises from below. These zones provide localized chemical gradients that certain microorganisms exploit, creating microhabitats that support small communities. In addition to amphipods, Baikal hosts a remarkable diversity of sponges. Freshwater sponges exist in other lakes, but Baikal species are unusually large and structurally complex. The most iconic is Lubomirskia baikalensis. These sponges can form branching colonies that resemble underwater shrubs. They're often bright green due to symbiotic algae living within their tissues. The symbiosis is critical. The algae perform photosynthesis, providing nutrients to the sponge. In return, the sponge provides structure and access to light in clear water. This partnership has persisted for millions of years. In recent years, however, some Baikal sponges have exhibited signs of stress. Scientists observe discoloration and decay in certain regions, raising concerns about changing water chemistry or microbial imbalance. The health of these sponges is closely monitored because they are integral to local ecosystems. Then there are the fish. Baikal contains several endemic fish families, including the golomyanka. Golomyanka are unusual in several ways. They are translucent, almost ghost-like in appearance. Their bodies contain high fat content which helps them survive in cold, deep water. Unlike most fish, golomyanka are viviparous, meaning they give birth to live young rather than laying eggs. They inhabit deep zones and perform vertical migrations, moving toward the surface at night and descending again during the day. Because they are abundant and distributed across depths, they serve as a major food source for other species. Their translucent bodies seem adapted to low-light conditions, reducing visibility to predators. Another endemic fish group is the sculpins, particularly the Cotycomephorus species. These fish have adapted to cold, oxygen-rich water and display variations in body shape depending on depth. Some sculpins are benthic, living on the lake floor. Others occupy mid-water zones. Their diversification parallels that of amphipods, reflecting long-term adaptation to ecological niches. Perhaps the most famous endemic animal is the Baikal seal, or nerpa. Seals are marine mammals, Baikal is freshwater, and yet, around 100,000 seals live entirely within the lake. The nerpa's presence continues to intrigue researchers. Genetic evidence suggests their ancestors entered Baikal during glacial periods, when connections between Arctic marine systems and inland waters may have existed through river networks. Once isolated, the seals adapted fully to freshwater life. They feed primarily on golomyanka and other endemic fish. They breed on ice during winter, relying on stable ice cover for pup survival. The Nerpa is the only exclusively freshwater seal species in the world. Its continued survival depends on ice duration and fish populations. As ice seasons shorten and temperatures shift, scientists monitor reproductive success carefully. Beyond visible animals, Baikal's microbial world is equally distinctive. Bacteria and archaea adapted to cold, oxygen-rich depths contribute to nutrient cycling. Some strains are unique to the lake's hydrothermal zones. Microbial diversity in deep sediment layers may include lineages that have persisted for millions of years, surviving in isolation. Genomic sequencing projects aim to catalogue these microorganisms, not only to understand Baikal's ecology, but also to explore biochemical pathways that may have broader applications. In an environment where pressure is high and temperature is near freezing, enzymes must function efficiently. Studying such enzymes can inform biotechnology and industrial processes. Isolation also leads to fragility. Endemic species often lack defences against invasive competitors. Because Baikal's ecosystem evolved in relative isolation, introduced species could disrupt established food webs. In recent decades, scientists have expressed concern about invasive algae and small crustaceans entering through shipping or human activity. Even minor introductions can have disproportionate effects in systems that evolved without exposure to such organisms. Baikal's long-term stability allowed specialization. Specialization reduces flexibility. For example, certain amphipods thrive only within narrow temperature ranges. If surface waters warm beyond those ranges for extended periods, population shifts could occur. Similarly, fish adapted to cold, oxygen-rich water may struggle if vertical mixing patterns change and oxygen levels fluctuate. Evolution over millions of years created a finely balanced network. The sheer age of the lake means some species have evolutionary histories extending back further than many terrestrial ecosystems around it. Comparative genetic studies suggest that some Baikal lineages diverge from their closest relatives tens of millions of years ago. That timeline places their origin long before modern humans appeared. When researchers analyse sediment cores, they sometimes find fossilized remains of ancient diatoms, microscopic algae that record past environmental conditions. Many diatom species in Baikal are endemic as well. Their silica shells accumulate in sediment, forming part of the geological archive. The diversity of diatoms reflects adaptation to seasonal cycles, light penetration, and nutrient availability specific to Baikal. In some cases, diatom lineages appear to have evolved continuously within the lake since its early formation. Such continuity is rare. In younger lakes, diatom communities often change completely after glaciation events. Baikal's depth protected it from total erasure during ice ages. Ice covered the surface at times, but the deep basin persisted, preserving life in lower layers. That persistence allowed species to survive climatic extremes that extinguished organisms elsewhere. But survival under past natural variability does not guarantee survival under rapid anthropogenic change. Researchers studying Baikal often describe it as a natural laboratory for evolution. Because of its isolation and age, it offers insight into how ecosystems diversify over geological timescales. Yet it is not a sealed laboratory. Human presence along the shore has increased. Tourism brings visitors who marvel at clear water and unique wildlife. With visitors come infrastructure, waste, and potential contamination. Scientists collaborate with local authorities to monitor nutrient input, invasive species, and habitat disruption. They conduct long-term population studies of key species, tracking abundance and reproductive success. The Nerpa population, for instance, is estimated periodically through aerial surveys and tagging studies. Amphipod diversity is assessed through benthic sampling at various depths. Sponges are examined for signs of disease or stress. Even subtle shifts in microbial communities are documented. The reason for such vigilance is straightforward. When a species exists nowhere else, its extinction is permanent. There is no neighbouring lake to recolonize from, no external reservoir. The entire global population resides within one basin. That reality adds weight to scientific discussions. Baikal's creatures are not just regional curiosities, they are unique evolutionary outcomes. There is also an emotional component, though scientists rarely frame it that way. Diving beneath the surface and seeing forests of green sponges swaying gently in clear water, knowing they evolved in isolation for millions of years, can be striking. Observing a nerpa resting on winter ice, entirely dependent on conditions within a single lake, underscores interconnectedness. Watching amphipods scatter across sediment at depths exceeding a kilometer reminds researchers that life adapts in ways that seem improbable until observed. The lake's biodiversity challenges assumptions about freshwater limitations. It demonstrates that with time and stability, even inland basins can rival islands and oceans in evolutionary richness. Yet richness is not permanence. Because these species evolved under specific conditions, cold water, stable oxygenation, long ice seasons, any alteration in those parameters can ripple outward. Climate projections for Siberia indicate continued warming trends. Warmer winters mean thinner ice. Thinner ice affects nerpa breeding success. Altered surface temperatures affect plankton timing. Plankton shifts influence fish feeding. Fish population changes affect seals and birds. The web is intricate. Scientists do not predict immediate collapse, but they acknowledge uncertainty. Long-term ecological stability can mask tipping points until they are crossed. One of the unsettling aspects of Baikal's biodiversity is precisely how unique it is. Unique systems are difficult to replace. They cannot be restored easily if disrupted. Once a lineage that evolved over millions of years disappears, it is gone in a time frame that dwarfs human planning horizons. This awareness drives ongoing research and conservation efforts. International collaborations bring funding and expertise to study Baikal's organisms in detail. Genetic libraries are built. Population baselines are established. Monitoring stations record temperature, chemistry, and biological indicators. The aim is not merely to catalogue species, it is to understand how they function within the whole. Because Lake Baikal is not defined solely by its depth or age. It is defined by life that filled that depth and adapted to that age. Life that does not exist anywhere else. And as researchers continue to study these organisms, they remain aware that the same tectonic forces that created the basin and the same climatic forces that shaped its stability are still active. The creatures of Baikal evolved under conditions that persisted for tens of millions of years. Whether those conditions can persist through the next few centuries is a question that lingers quietly beneath every survey, every dive, and every dataset gathered from the clear, cold water of the deepest freshwater lake on Earth. Among all the unusual life forms in Lake Baikal, one stands apart in a way that even seasoned biologists find difficult to explain at first glance. A seal, not near a coastline, not in brackish estuaries, not in an inland sea connected to an ocean. A true seal, fully marine in ancestry, living entirely within a freshwater lake thousands of kilometres from the nearest saltwater body. The Baikal seal, known locally as the nerpa, is the only exclusively freshwater seal species on Earth. There are other seals that tolerate freshwater for periods of time, and a few populations in places like the Caspian Sea that inhabit brackish environments. But the nerpa's entire life cycle unfolds within Lake Baikal. No migrations to the ocean, no seasonal returns to saltwater, just the lake. At first encounter, a nerpa does not appear extraordinary. It looks like a small rounded seal with large dark eyes and a thick layer of blubber suited for cold water. Adults typically weigh between 50 and 130 kilograms. Their fur is grey to dark brown, lighter on the underside. They move with familiar seal awkwardness on land and with streamlined grace in water. Nothing about their appearance suggests geological improbability, and yet their presence demands explanation. Seals are pinnipeds. Their ancestors evolved in marine environments. Their physiology, including salt regulation and feeding strategies, is adapted primarily to saltwater ecosystems. So how did a marine mammal end up in an isolated freshwater lake in Siberia? Scientists have debated this question for decades. The most widely accepted theory involves glacial periods and ancient river connections. During the Pleistocene ice ages, massive ice sheets covered large portions of the northern hemisphere. River systems shifted. Waterways expanded and contracted. It is believed that ancestors of the Nerpa may have migrated inland through connected river networks from Arctic marine environments. The Arctic Ocean connects to large Siberian rivers such as the Yenisei and Lena. At various times in geological history, water levels and ice coverage may have allowed marine mammals to travel further inland than they can today. Eventually, a population could have reached Lake Baikal. Once isolated, those seals would have faced new conditions: fresh water instead of salt water, different prey species, long periods of ice cover, and no marine predators. Genetic analysis supports the idea that Baikal seals are closely related to Arctic ringed seals. Molecular clock estimates suggest divergence occurred hundreds of thousands to a few million years ago, depending on the study. The timeline is still debated. What is not debated is that once isolated, the Nerpa adapted completely to freshwater life. Marine mammals drink seawater and excrete excess salt through specialized kidneys. In freshwater, the osmotic balance shifts. The body must prevent excessive water intake rather than eliminate salt. The Nerpa's kidneys function efficiently under freshwater conditions. Over evolutionary time, natural selection favored individuals best suited to the lake's chemistry. Diet also shifted. Baikal seals feed primarily on endemic fish species, especially golomyanka and sculpins. These fish inhabit various depths, and Nerpa are capable divers. Diving behavior studies show that Baikal seals routinely descend to depths of several hundred meters, with some recorded dives exceeding 500 meters. That is substantial for a freshwater mammal. Cold water and high pressure are not obstacles for them. Their thick blubber provides insulation. Their oxygen storage capacity in blood and muscle allows extended dives. In winter, ice becomes central to their life cycle. Lake Baikal typically freezes from January to May, though ice duration has shortened in recent decades. During this frozen period, Nerpa maintain breathing holes through the ice. They use their strong claws to keep these holes open. Breeding occurs on the ice. Females give birth to a single pup, usually in late winter. The pups are born with white fur, providing camouflage against snow-covered ice. This white coat, known as lanugo, is shed after several weeks. Ice stability is crucial during this period. If ice breaks up too early, pups may not be ready to swim long distances. They rely on the ice platform for protection from cold water and potential disturbances. Because Baikal is the only habitat for the species, breeding success directly influences global population stability. Population estimates suggest around 100,000 individuals currently inhabit the lake, though numbers fluctuate. Researchers monitor seal populations through aerial surveys, tagging programs, and acoustic studies. Despite their isolation, Nerpa do not appear genetically impoverished. Genetic diversity studies indicate sufficient variation within the population, suggesting that the founding group was large enough or that gene flow persisted for a considerable time before complete isolation. Still, being confined to one lake introduces risk. Any large-scale environmental change within Baikal would affect the entire species. This concentration of vulnerability is one reason scientists view the Nerpa with a mixture of admiration and concern. Their existence demonstrates evolutionary flexibility. Their confinement underscores fragility. Seals are typically top predators within their ecosystems. In Baikal, Nerpa occupy that role. They regulate fish populations and influence food web dynamics. By consuming golomyanka and sculpins, they help maintain ecological balance. In turn, their health reflects the health of lower trophic levels. Researchers analyse seal blubber and tissue samples to detect contaminants such as heavy metals and persistent organic pollutants. Because NERPA accumulate substances from their prey, they serve as bioindicators of water quality. Historically, industrial activity along parts of Baikal's shore raised concerns about chemical discharge. Monitoring of seal tissue provided insight into pollutant levels. Over time, regulations reduced some sources of contamination, but vigilance remains necessary. There have been unexplained mortality events. In certain years, researchers documented higher than normal numbers of dead seals washing ashore. Investigations examined potential causes, including viral infections, toxin exposure, and starvation. One suspected pathogen was canine distemper virus, which can infect pinnipeds. Disease outbreaks in isolated populations can spread quickly. Because NERPA do not mix with other seal populations outside Baikal, their exposure to marine pathogens is limited. However, contact with domestic animals or human activity around the lake could introduce novel diseases. Another variable is climate. Shorter ice seasons may disrupt breeding. Warmer water temperatures could influence fish distribution. If key prey species decline or shift depth ranges, seals may need to adjust hunting strategies. So far, NERPA have shown resilience, but resilience has limits. What makes their presence particularly striking is the psychological disconnect. When people imagine seals, they imagine coasts, waves, and salt spray. Lake Baikal sits more than 1,500 kilometers from the nearest ocean. The idea of a seal swimming beneath thick freshwater ice in the middle of Siberia challenges intuitive geography. It is not mythical, it is documented biology, and yet it feels misplaced, as though an ocean creature wandered too far inland and never left. The NERPA's round, expressive face has made it a symbol of Baikal. Local communities value it culturally. Historically, seals were hunted for meat, fur, and oil. Today, hunting is regulated. Conservation status assessments classify the species as of least concern globally due to stable numbers, but its unique habitat means local changes carry disproportionate weight. Unlike marine seals, which can relocate across vast oceanic distances, NERPA have nowhere else to go. Researchers using satellite tags have tracked seal movements across the lake. Some individuals travel long distances seasonally, moving between feeding areas and breeding sites. Despite the lake's size, it remains a closed system. Movement is horizontal within boundaries, not outward beyond them. There is also evidence that NERPA adjust diving behaviour based on prey availability and temperature gradients. During summer stratification, fish distribution shifts vertically. Seals follow. Their ability to exploit deep-water prey connects them directly to the lake's extreme depth. Few freshwater mammals operate at such vertical ranges. The relationship between NERPA and golomyanka is particularly interesting. Golomyanka are lipid-rich fish that produce live young. They inhabit mid-water and deep zones. Their fat content makes them energy-dense prey. In turn, the seal's blubber thickness reflects availability of such prey. This predator-prey relationship evolved entirely within the confines of Baikal. No external migration replenishes stocks. The system is self-contained. From an evolutionary perspective, the NERPA represents a case study in rapid adaptation relative to geological timescales. If divergence from marine ancestors occurred within the last million years, then in evolutionary terms the transition to freshwater life happened relatively quickly. Physiological flexibility allowed survival. Behavioural adjustments ensured reproductive success under ice-covered conditions. Over time, freshwater specialisation became complete. It is also possible that seals reached Baikal more than once, reinforcing genetic diversity during periods when connections to marine systems were more open. Sediment records indicate fluctuating water levels and climatic shifts that may have influenced river pathways. Even so, once isolated, the species committed fully to the lake. there is no evidence of regular migration back to the Arctic in modern times. One aspect that continues to intrigue researchers is how seals navigated to Baikal originally. River routes connecting Arctic waters to inland basins are complex. During glacial maxima, ice dams and altered drainage patterns could have created temporary corridors. Reconstructing these paleohydrological networks is challenging. Yet the presence of NERPA serves as living evidence that such a pathway existed at some point. Their continued survival demonstrates that Baikal's ecosystem has been sufficiently productive to sustain a large mammalian predator for thousands of years. The lake's fish biomass supports this. While some fish species are endemic and relatively small, their numbers are substantial. Golomyanka, for instance, are estimated to make up a significant proportion of the lake's total fish biomass. Because they inhabit deep zones and perform vertical migrations, they form an accessible food source for diving seals. The clarity of Baikal's water may also aid hunting. High visibility allows seals to detect prey more easily compared to turbid environments. However, at deeper depths, darkness limits reliance on vision. Seals possess sensitive whiskers, or vibrissae, capable of detecting minute water movements caused by swimming fish. This sensory adaptation is common among pinnipeds and functions effectively in Baikal's deep, dark zones. In winter, breathing holes become lifelines. Seals maintain multiple holes across their territories. Females often create snow-covered layers on the ice for pupping, providing insulation and concealment. Snow cover quality influences layer stability. If snow is insufficient due to warmer winters, layers may collapse or offer less protection. Researchers track ice thickness and snow accumulation as part of seal population monitoring. The interplay between ice, temperature, prey and disease forms a web of variables affecting NERPA survival. Their existence is not an isolated curiosity. It is a dynamic indicator of Baikal's overall condition. From a broader perspective, the NERPA underscores how Baikal blurs boundaries between freshwater and marine systems. Hydrothermal vents, extreme depth, methane hydrates, endemic crustaceans, and a freshwater seal all coexist within a continental rift lake. Each element alone might be explained. Together they form a system that feels almost misplaced in standard ecological categories. Scientists do not describe the NERPA as terrifying, but they do recognise that its presence amplifies the uniqueness of Baikal. A lake that can sustain an entire seal species for hundreds of thousands of years must be extraordinarily stable. A lake that might face rapid environmental shifts places that species in a precarious position. The NERPA swims beneath winter ice, surfaces through carefully maintained breathing holes, hunts in cold depths, and raises its young on frozen platforms. It does so unaware of tectonic forces pulling the continent apart, unaware of global climate trends, unaware of industrial history along the shoreline. Its existence is a product of long geological patience and evolutionary opportunity. Whether that patience can continue uninterrupted depends not only on natural forces, but increasingly on human decisions surrounding one of the most ancient freshwater systems on Earth. And the fact that a seal that should not exist thrives there at all only deepens the sense that Baikal is less a simple lake and more an ongoing geological and biological anomaly, still unfolding in ways that continue to challenge expectations. When winter settles over southern Siberia, Lake Baikal does something that transforms it completely. It hardens. By January, the surface begins to freeze. At first, thin sheets form along sheltered bays. Then the ice thickens, spreads, and locks the entire lake beneath a solid lid that can reach more than a metre in thickness. From above, it can look motionless, but the ice is anything but silent. People who spend time on Baikal in winter often describe hearing it before they understand it. Deep, resonant booms echo across the frozen expanse. Sharp cracks snap like distant rifle shots. Low rumbles travel beneath the surface, vibrating through boots and bones. It sounds as if the lake is shifting in its sleep. The explanation is physical, not mystical. Ice expands and contracts with temperature. During the day, sunlight can warm the surface slightly, even in sub-zero air. At night, temperatures drop sharply, sometimes below -30 degrees Celsius. These fluctuations cause the ice sheet to expand and contract unevenly. When stress builds beyond a threshold, the ice fractures. Because Baikal is enormous, more than 600 kilometers long, these fractures can extend for kilometers. Some cracks are narrow and hairline, others open into jagged seams wide enough to notice from a distance. The sound of cracking ice carries far across the frozen surface. Cold, dense air transmits low-frequency vibrations efficiently. A fracture occurring kilometers away can echo like thunder. That is why winter visitors often describe the lake as groaning or breathing. It is simply physics acting on a massive scale. But the scale matters. Most lakes freeze quietly. They are smaller, shallower, less subject to dramatic internal stress. Baikal's vast surface area and depth create conditions where pressure differences can build significantly. Wind also plays a role. Even under ice, water continues to move. Currents shift beneath the frozen lid, pushing against it from below. When winds sweep across the surface, they can create pressure ridges where ice sheets collide and buckle. These ridges sometimes rise several meters above the flat surface, forming jagged walls of broken ice slabs stacked against one another. In certain regions, cracks form in long, nearly straight lines tracing underlying structural features. Some fractures follow fault lines beneath the lake, subtle reminders that tectonic forces continue below. The ice also records methane. As mentioned earlier, methane seeps upward from sediment in certain areas. In winter, when the surface freezes, rising methane bubbles can become trapped within the forming ice. The result is striking. Columns of bubbles freeze in place, forming vertical stacks that appear like strings of pearls suspended in crystal. Photographs of these frozen methane formations circulate widely, often accompanied by exaggerated claims about explosive danger. In reality, most methane release is gradual and not catastrophic. Still, the visual effect reinforces the idea that something is active below. The ice is transparent in many areas, especially early in the season before snow accumulates. Baikal's water clarity extends upward into its frozen state. When conditions are right, people walking across the ice can see meters below, observing rocks, trapped bubbles, and even fish moving beneath. That transparency contributes to the sensation that the lake is not asleep but paused. It also means that changes in ice thickness are visible. Scientists measure ice thickness annually as part of long-term monitoring programs. Historical records indicate that average ice cover duration has decreased in recent decades. Ice now forms later and melts earlier than it did in the early 20th century. This trend is consistent with broader warming patterns observed across Siberia. Ice is more than a seasonal curiosity. It is central to Baikal's ecosystem. For the Nerpa, stable ice is essential for breeding. Females give birth on the ice and create snow layers for protection. If ice becomes unstable too early, pup mortality can increase. For certain microorganisms and plankton species, ice influences light penetration and water temperature. Transparent ice allows sunlight to reach underlying water, supporting winter phytoplankton blooms. These blooms provide early season food for zooplankton. In spring, when ice breaks up, mixing events redistribute nutrients. Thus, ice acts as both barrier and regulator. The groaning sounds that echo across winter Baikal reflect constant adjustment. Ice sheets are not static. They shift slightly under stress. Expansion during warm periods presses against contraction during cold spells. Pressure ridges accumulate where movement is constrained. Sometimes large cracks open suddenly, forming leads, narrow channels of open water within the ice field. These leads can freeze again quickly in extreme cold, leaving layered structures visible from above. Researchers studying ice dynamics use satellite imagery to map these patterns. Thermal imaging reveals temperature differences across the surface. drones capture high-resolution views of crack networks. One recurring phenomenon that attracts attention is the formation of large circular patterns in the ice. These rings, sometimes spanning 5 to 7 kilometers in diameter, are visible from space. At first glance, they appear almost artificial. Scientists have linked these formations to underwater convection currents. When slightly warmer water rises from deeper zones, it can thin ice locally. Combined with wind patterns and temperature gradients, this can produce circular stress fields. The rings are not perfectly uniform, but they are consistent enough to track. Their appearance varies year to year depending on conditions. Such features underscore how closely surface ice interacts with deeper water dynamics. The lake does not freeze uniformly from top to bottom. Below the ice, water remains liquid, cold but mobile. In some winters, thick snow cover insulates the ice, slowing thickening. In others, clear, cold conditions allow ice to grow thicker and more transparent. Variability is normal. What concerns scientists is long-term trend. If winter temperatures continue to rise, average ice thickness may decline. Reduced ice stability affects breeding platforms for seals and alters under-ice ecological processes. There is also an acoustic dimension to ice behaviour. Hydrophones placed beneath the ice capture sounds transmitted through the water. Researchers have recorded crack propagation events and ice movement from below. These acoustic signatures help scientists understand stress distribution and fracture mechanics. The sound of cracking ice is not random noise. It carries information about structural integrity. When large cracks propagate rapidly, they release energy in low-frequency pulses that travel across the lake. Standing alone on the ice during such an event can be unsettling. The surface beneath your feet may appear solid and unbroken. Then, without warning, a sharp report echoes across the expanse, followed by a long, resonant hum. The crack may be kilometers away, but the sound suggests proximity. Visitors sometimes describe the sensation as the lake speaking. In reality, it is a massive sheet of frozen water adjusting to environmental forces. Another feature of Baikal's winter landscape is the formation of ice caves along rocky shorelines. When waves freeze against cliffs early in the season, layered structures form. As temperatures fluctuate, ice expands and contracts, shaping translucent arches and tunnels. These formations are temporary and can collapse unexpectedly. They attract photographers and tourists, but they are also reminders of instability. Even when ice appears thick and solid, conditions can change rapidly. Local authorities issue advisories each winter regarding safe travel routes across the lake. Vehicles do cross certain sections, especially where ice thickness exceeds established safety thresholds. Still, every winter sees incidents where vehicles fall through thin ice near leads or warm current zones. Underneath, currents continue to flow. Baikal's depth influences ice behaviour as well. In shallower lakes, bottom friction can dampen water movement under ice. In Baikal, deep water allows more dynamic circulation beneath the frozen surface. This circulation can create localised thinning. Scientists use instruments called thermistor chains to measure temperature profiles from surface to depth. Data show that even in winter, small temperature gradients persist. Those gradients drive subtle convective currents. Wind stress on the ice surface can also translate into water movement below. Because the ice sheet covers such a vast area, wind can generate large-scale stress fields. When stress exceeds tensile strength, cracks form. Cracks often follow predictable orientations based on wind direction and shoreline geometry. Over time, networks of fractures create patterns visible from satellites. Monitoring these patterns helps researchers understand changing winter dynamics. Beyond physical processes, winter ice shapes human interaction with the lake. Historically, frozen Baikal served as a transportation route. Sledges and later vehicles crossed from one shore to another, shortening travel distances. During World War II, ice roads supported supply routes. Today, winter tourism has increased. People drive onto the ice to reach remote villages or scenic points. This human presence adds complexity. Increased traffic can stress ice locally. though the overall scale remains small compared to natural forces. Still, more visitors mean greater need for safety education. From a scientific perspective, winter provides unique research opportunities. Ice cover allows stable platforms for drilling and instrument deployment. Sediment cores are sometimes extracted through holes drilled in ice. Hydrophones and temperature sensors can be placed more easily when waves are absent. At the same time, cold conditions challenge equipment reliability. Electronics must withstand extreme temperatures. Fuel gels in machinery. Logistics become demanding. The image of Baikal in winter often focuses on beauty. Clear blue ice, trapped bubbles, mirrored skies. The sounds are less frequently captured in photographs. Yet those sounds are integral to understanding the system. Groans, cracks, and rumbles indicate stress redistribution. They reflect the interplay between atmospheric temperature, wind, water movement, and underlying geology. Even tectonic activity can influence ice. An earthquake beneath the lake in winter can propagate stress through the water column and into the ice sheet. Though rare, such events have been recorded. Ice responds immediately to shifting forces below. For scientists studying climate change, Baikal's ice record provides valuable data. Long-term observations of freeze-up and break-up dates offer insight into regional warming trends. Comparisons with sediment cores help contextualize modern changes within millennial variability. If ice duration decreases beyond historical ranges observed in sediment proxies, that shift becomes significant. Ice groans not because it is alive, but because it is under tension. That tension is seasonal, mechanical, and increasingly climatic. The breathing sensation people describe often corresponds to expansion during warming periods followed by contraction during rapid cooling. Ice seems to inhale and exhale as temperatures fluctuate. This breathing is measurable. Sensors record expansion rates and contraction cycles. From a distance, the frozen lake appears inert. Up close, it reveals constant adjustment. Cracks form and seal. Pressure ridges rise and settle. Bubbles freeze and remain suspended. And beneath it all, cold water continues to move slowly in darkness. For the Nerpa, the ice is home and nursery. For plankton, it is filter and lens. For scientists, it is both barrier and window. As climate patterns shift, the ice will likely change with them. Thinner sheets may groan differently. Crack networks may reorganize. Breathing holes for seals may become less reliable. These possibilities drive continued monitoring. Because in a system as old and deep as Baikal, winter ice is not just seasonal decoration. It is a structural component of the ecosystem. And when that structure begins to shift in duration or strength, the sounds that echo across the frozen surface may become more than atmospheric temperature adjusting ice. They may signal broader transformations unfolding within one of the most ancient freshwater systems on Earth, where even the stillness of winter carries evidence of forces moving quietly below. In certain winters, when satellites pass over southern Siberia and capture images of Lake Baikal's frozen surface, something unusual appears. Not cracks, not pressure ridges, circles, perfectly round or nearly round rings etched into the ice, sometimes 5, 6, even 7 kilometers across. Darker in tone than the surrounding white or pale blue surface, these rings stand out sharply against the vast frozen expanse. At first glance they look deliberate, too symmetrical to be random, too large to ignore. The first time such images gained international attention, speculation spread quickly. Some suggested meteor impacts beneath the ice. Others whispered about mysterious energy sources, or even something less grounded in geology. Scientists, as they tend to do, looked for physical explanations, and they found them. But the explanation, while grounded in physics, does not make the phenomenon any less striking. To understand the rings, it helps to imagine the lake not as a frozen slab, but as a dynamic system temporarily sealed. Beneath the ice, water continues to move. Even in winter, Lake Baikal is not static. Its immense depth allows temperature gradients to persist. Slightly warmer water, only fractions of a degree above the surrounding temperature can rise from deeper zones due to convection currents. These currents are influenced by underwater topography and in some areas by hydrothermal activity. Where warm water rises, it interacts with the ice above. Ice thickness is not uniform across the lake. It varies depending on temperature, wind, snow cover, and water movement below. When a convection cell forms beneath the ice, warmer water can thin the ice locally. If that convection cell rotates slowly, driven by Coriolis forces or shaped by underwater ridges, it can create a circular pattern of stress. The result is a ring where ice either melts slightly earlier, forms differently, or fractures along curved boundaries. From ground level, these rings are not always obvious. They may appear as subtle variations in ice thickness or as zones where the surface looks slightly darker due to meltwater pooling. From space, however, the pattern becomes unmistakable. Satellite imagery from agencies such as NASA and the European Space Agency has documented multiple ring formations over the years. The rings do not appear every winter. They are sporadic, influenced by specific combinations of temperature, wind, and subsurface currents. Researchers studying these events analyze temperature data, bathymetric maps, and current measurements. They found that rings often occur above underwater ridges or fault zones, where slight geothermal heat flux contributes to convection. Hydrothermal vents, while not as dramatic as oceanic black smokers, can provide localized heat. Even a small temperature difference, on the order of tenths of a degree, can influence ice formation over time. Water that is slightly warmer than surrounding water is less dense. It rises slowly. As it reaches the underside of the ice, it transfers heat. That heat does not instantly melt large holes. Instead, it creates a thinning zone. If wind stress rotates the surface water before freezing, a circular current pattern can become established. When ice forms over such rotating water, stress distribution follows the circular motion. As temperatures fluctuate, expansion and contraction accentuate these boundaries. The darker appearance of the rings often results from thinner ice, allowing underlying water to show through more clearly, or from meltwater accumulating along the circle. Scientists have deployed temperature sensors and current meters in areas where rings formed. Data confirm subtle but measurable differences in heat flow and circulation beneath these zones. One particularly well-studied ring appeared in April 2009. Satellite imagery showed a dark circle in the southern basin of Baikal. Researchers correlated its position with known underwater topography. Subsequent modelling supported the convection hypothesis. Despite this explanation, there remains a sense of quiet unease when looking at those images. A ring several kilometres wide implies coordinated movement over large scales. It suggests that the lake's interior processes can organise surface features visible from orbit. Most lakes do not display such patterns. The combination of extreme depth, rift-induced topography, and seasonal ice cover makes Baikal uniquely suited to this phenomenon. There is also an acoustic dimension. Ice-cracking events sometimes follow the perimeter of these rings, as stress concentrates along boundaries of differing thickness. Field reports describe hearing amplified cracking sounds near ring edges. Cracks may radiate outward or trace curved paths. For those standing on the ice without knowledge of subsurface currents, the experience can feel unpredictable. Beyond the physical explanation, the rings highlight how intimately connected Baikal's surface is to its depths. The lake's geology influences its hydrodynamics. Hydrodynamics influence ice formation. Ice formation creates visible signatures. Each layer communicates with the next. The rings also remind scientists that hydrothermal activity, though subtle, plays a measurable role in the lake's winter behaviour. Hydrothermal vents in Baikal release warmer water enriched with minerals and gases. While most vent sites are localised, their influence can extend beyond immediate surroundings through slow circulation. Mapping these vent fields remains ongoing. Submersibles have identified several vent clusters at depths exceeding 1,300 metres. These vents support microbial communities adapted to chemical energy sources. Though not directly responsible for all ring formations, geothermal heat contributes to convection patterns that shape ice behaviour. Climate change introduces another variable. If average winter temperatures rise, ice thickness may decrease overall. Thinner ice is more responsive to subsurface heat and surface wind stress. Future winters may see changes in ring frequency or distribution. Monitoring satellite imagery year after year allows researchers to track such patterns. One challenge in studying these rings is their transient nature. By late spring, as temperatures rise, the ice begins to break up. Rings disappear as the frozen surface fragments into drifting flows. Direct sampling opportunities are limited to a narrow seasonal window. Field expeditions must coordinate precisely to access ring sites before breakup. In some cases, researchers drill holes along ring boundaries to measure thickness differences. Ice cores extracted from within rings and outside them reveal structural variations. Thinner, more crystalline ice often corresponds to ring zones. This structural difference influences strength. Vehicles crossing Baikal in winter are advised to avoid areas near visible ring patterns, as thinner ice may not support heavy loads. Local authorities monitor known hotspots when issuing travel advisories. The rings have become a seasonal curiosity among photographers and tourists. Drone footage captures sweeping arcs etched into pale blue expanses. Yet behind the visual appeal lies complex fluid dynamics shaped by one of Earth's deepest freshwater basins. Some rings appear incomplete, more like arcs or crescents. This variability reflects differences in wind direction and current intensity. Not all convection cells produce symmetrical outcomes. In certain years, multiple rings appear simultaneously in different basins. Their distribution often aligns with known structural features beneath the lake. The central basin, being deepest, exhibits ring formation more frequently than shallower zones. This correlation supports the idea that depth-driven circulation contributes to the phenomenon. Researchers continue refining models that simulate heat transfer between deep water and ice. These models incorporate bathymetry, geothermal heat flux, wind stress, and atmospheric temperature patterns. The goal is to predict where rings might form under given conditions. Understanding such dynamics is not merely academic. It contributes to broader knowledge of how large freshwater systems respond to climatic and tectonic influences. Baikal functions as a case study in interactions between deep water circulation and seasonal ice. Insights gained here may apply to other cold region lakes experiencing warming trends. Still, there is something visually arresting about those circles. They do not resemble chaotic fracture networks common on frozen lakes. They appear deliberate. The human mind gravitates toward patterns. A circle suggests design. Yet the explanation rests firmly in natural processes. Warm water rises, cold water sinks, wind rotates surface layers, ice responds to stress, scale amplifies effect. Because Baikal is so vast and deep, subtle forces manifest in grand geometry. That geometry becomes visible only under specific winter conditions. It is a reminder that even when frozen, the lake is active. Energy moves beneath the surface. Heat from Earth's interior contributes fractionally but persistently. Water circulates slowly in dark depths. Ice, sensitive to both atmosphere and lake, records those movements in shape. Scientists studying the rings approach them with curiosity rather than alarm. They represent natural variability within a dynamic system. However, as with ice duration and thickness, long-term changes in ring behaviour could indicate shifting subsurface dynamics. If convection patterns alter due to warming or tectonic adjustments, surface expressions may change. Each ring becomes a seasonal snapshot of hidden movement. The circles in the ice are not warnings, they are signatures. They mark where depth communicates with winter, where rift energy and atmospheric cold intersect. And they illustrate once again that Lake Baikal cannot be understood solely from the shoreline. Its processes extend from tectonic fractures kilometers below sediment to thin ice cracking under Siberian stars. Even when the lake appears sealed and silent, patterns visible from space reveal that forces continue to shape it quietly, beneath a frozen surface that only seems still. There are moments in scientific exploration when instruments capture something unexpected. Not something supernatural, not something inexplicable, just something that does not fit neatly into what researchers anticipated seeing. In Lake Baikal, a handful of such moments have involved light. Reports of faint glows, unusual flashes, and brief luminous phenomena beneath the surface have circulated for decades. Some originated with divers, others with submersible crews, a few with researchers analysing underwater footage in laboratories long after expeditions ended. Before speculation takes over, it is important to clarify something. There is no verified evidence of mysterious civilizations or unidentifiable objects hiding in Baikal's depths. The lights that scientists have observed have plausible explanations grounded in physics and biology, and yet, the combination of extreme depth, cold darkness, and occasional illumination creates an atmosphere that feels different from typical freshwater lakes. Most lakes are not dark enough, deep enough, or remote enough to produce stories of a light beneath the surface. Baikal is. The first factor to consider is bioluminescence. In marine environments, bioluminescent organisms are common. Plankton, jellyfish, and certain fish species emit light through chemical reactions involving luciferin and luciferase. These reactions produce cold light without heat. Freshwater systems rarely host bioluminescent species at scale. In Baikal, true bioluminescence is not widespread like it is in oceans. However, certain microorganisms and bacteria can emit faint light under specific conditions. Laboratory studies have documented weak luminescent activity in some Baikal microbial strains. The intensity is extremely low, not bright enough to illuminate large areas, but in total darkness at great depth, even faint emissions can appear noticeable. Divers descending into the lake's deeper zones describe a gradual loss of ambient light. At several hundred meters, sunlight disappears completely. Artificial lights from submersibles or dive equipment become the only illumination. In that environment, reflective surfaces can produce surprising visual effects. Many deep-dwelling amphipods and fish have semi-translucent or reflective tissues. When a submersible spotlight sweeps across them, light can scatter unpredictably, creating flickers that seem to move independently. This can be disorienting for observers unaccustomed to deep-water optical behaviour. Another source of light involves methane. When methane bubbles rise from sediment and reach shallower zones, they sometimes interact with ice or pressure changes. Methane itself is not luminous underwater. However, if methane accumulates in confined spaces and is exposed to certain mechanical disturbances, it can produce brief flashes due to triboluminescence or electrical discharge. These occurrences are rare and typically subtle. More commonly, reports of lights correspond to electrochemical reactions triggered by tectonic stress. In certain geological settings, mechanical stress on rocks can generate electrical charges. This phenomenon, sometimes called piezoelectricity, occurs when specific minerals, such as quartz, are compressed or fractured. Lake Baikal lies within an active rift zone. Earthquakes, even minor ones, release stress along faults. Some researchers have proposed that under particular conditions, stress-induced electrical activity could produce faint luminous phenomena underwater, especially near fault lines. This concept remains under investigation. Earthquake lights have been documented in other parts of the world, typically appearing in the sky above seismic zones. Underwater manifestations are more difficult to confirm. Submersible missions in Baikal during the early 2000s occasionally recorded unusual flashes in deep zones. Subsequent analysis often attributed these to mechanical disturbances, equipment reflection, or sediment particles interacting with light beams. In some cases, mineral-rich vent emissions created shimmering visual effects when illuminated. Hydrothermal vents release warmer water containing dissolved minerals. When this mineral-laden water mixes with colder surrounding water, microcrystals can precipitate. These particles scatter light. Under submersible spotlights, such scattering can appear as glowing clouds or flickering halos. The human eye, especially when adjusted to darkness, can interpret scattered light as originating from within the water rather than from an external beam. There are also optical illusions related to thermoclines. Though Baikal's deep waters are relatively stable in temperature, slight gradients exist. When light passes through layers of differing density, refraction occurs. This bending of light can distort objects, creating shimmering or wave-like effects that appear luminous. In extremely clear water like Baikal's, refraction artifacts can be pronounced. One often cited account involved divers who reported seeing faint glows near the lakebed during nighttime research dives. Subsequent investigations suggested that certain bacterial colonies around hydrothermal vents emitted weak luminescence. In total darkness, with no competing light sources, these emissions can appear brighter than they actually are. It is worth remembering that the human visual system is highly sensitive to contrast in dark conditions. Even minimal light can seem significant when surrounded by blackness. Baikal's depth ensures that below several hundred meters, complete darkness prevails unless disturbed by artificial light. In that darkness, even small bioluminescent emissions or reflective glints stand out. There is also the phenomenon of ice luminescence. During winter, electrical discharges within ice can produce faint blue glows along cracks. When ice fractures under stress, charges may build along edges. These charges can ionize air within small cavities, producing brief flashes. Observers on the ice sometimes report seeing bluish streaks accompanying loud cracks. Underwater, similar stress-induced electrical phenomena could occur along submerged ice boundaries. However, documented cases remain limited. Another factor involves sediment disturbance. When submersibles descend or currents shift near the lake floor, fine sediment becomes suspended. Under artificial lighting, these particles reflect and scatter beams in dynamic ways. To someone inside a submersible, moving through a cloud of illuminated sediment in darkness, the experience can resemble drifting through stars. Points of light move unpredictably, brightness fluctuates, perspective shifts. Without context, it could appear as though the lake itself emits light. Researchers trained in underwater optics understand these effects. Yet even experienced scientists sometimes describe deep dives in Baikal as visually unusual compared to other freshwater environments. Part of that difference lies in clarity. In murky lakes, light beams are quickly diffused. In Baikal, beams travel further before scattering. This creates sharper boundaries between illuminated and dark zones. Objects enter and exit the beam abruptly, enhancing contrast. There are also reports of phosphorescent glows observed during winter nights from the shoreline. Some residents have described faint bluish light beneath ice near certain areas. These accounts are anecdotal and not systematically verified. Possible explanations include light pollution reflecting through ice, distant vehicle headlights refracted through cracks, or natural gas emissions interacting with the electrical phenomena. Because Baikal is remote and sparsely populated along much of its shore, artificial light sources are limited. This amplifies the perceived intensity of any unusual illumination. From a scientific standpoint, no confirmed evidence supports large-scale, unexplained luminous activity in Baikal's depths. All documented cases to date have plausible physical or biological explanations, yet the lake's unique combination of depth, tectonic activity, hydrothermal vents, methane release, and seasonal ice creates conditions where light phenomena are more likely to attract attention. In a shallow lake, bioluminescent bacteria might go unnoticed. In Baikal's abyssal zones, faint glows appear dramatic. In a small pond, sediment scattering would be chaotic but confined. In Baikal, it unfolds against kilometers of black water. There is also the psychological dimension. Descending into one of the deepest freshwater bodies on Earth, knowing that beneath you lies sediment recording millions of years, and faults still shifting, influences perception. The mind becomes attuned to anomalies. Small flashes feel significant. Light has symbolic power in darkness. Scientists operating submersibles in Baikal often report heightened awareness of surroundings. The absence of external reference points, no coastline visible, no ambient light, creates a sensory environment unlike surface research. Artificial beams carve narrow tunnels through darkness. Anything entering that beam becomes a focal point. If a reflective amphipod swims through, it glitters momentarily. If methane bubbles drift upward and catch light, they shimmer. If mineral particles scatter illumination, they appear to glow. In post-dive analysis, video footage is reviewed carefully. Frames are examined for anomalies. In most cases, what initially seem mysterious resolves into identifiable physical causes. Still, the repetition of such reports contributes to the lake's reputation. Lights beneath the surface sound like folklore. In reality, they are byproducts of complex but explainable processes occurring in an environment rarely accessible to human senses. Baikal's depth and clarity combine to create dramatic contrast between light and dark. Hydrothermal chemistry introduces mineral clouds. Methane bubbles alter optical behavior. Tectonic stress may generate minor electrical effects. Biological luminescence, though faint, adds another layer. None of these elements alone would inspire speculation. Together, they create a setting where brief flashes and glows feel amplified. Researchers continue to study deep water optics and microbial luminescence in Baikal. Advances in low-light cameras and sensors improve documentation. As technology refines, explanations become clearer. The lake does not conceal supernatural light sources. It reveals how light behaves under pressure, cold, and geological activity. And in doing so, it reinforces the idea that even in a system defined by water and sediment, energy moves in subtle ways. The darkness beneath Baikal is not empty. It is a space where physical forces interact quietly, where biology adapts to low-light conditions, where heat from Earth's interior rises fractionally, where light, when it appears, carries information about those processes. In the end, the lights beneath the surface do not signal hidden threats. They signal complexity. And complexity in a lake already shaped by tectonic tension and evolutionary isolation adds one more layer to an environment that continues to surprise those who look closely enough into its depths. For all the sonar maps, sediment cores, remotely operated vehicles and manned submersibles that have descended into Lake Baikal, there is still a quiet truth that researchers acknowledge. We have not fully explored it. That statement does not mean that large portions of the lake are completely unmapped. Bathymetric surveys have charted its contours with increasing precision over the past decades. We know its maximum depth, its three main basins, the underwater ridges that separate them, and the approximate thickness of sediment beneath the water column. But mapping is not the same as knowing. The deepest parts of Baikal sit more than 1,600 meters below the surface. Beneath that water lies sediment reaching 7 kilometers or more in thickness, and beneath that sediment lies the thinned continental crust slowly pulling apart. When scientists say there are depths we still have not touched, they are speaking both literally and metaphorically. Literally because even with advanced submersibles, only select locations on the lake floor have been visited directly. The deepest points have been reached, yes. But the lake floor spans thousands of square kilometers. Sampling remains sparse compared to its size. Metaphorically, because each descent answers specific questions while raising others. The mere submersibles, originally built for deep ocean exploration, conducted several dives in Baikal during the late 2000s. They reached the deepest known point in the central basin, collecting sediment samples and capturing footage of the lakebed. What they found was not a barren abyss. They found slopes, sediment plains, fault scarps, and scattered life. Amphipods moved across the bottom. Microbial mats appeared near hydrothermal sites, methane bubbles rose from fissures in sediment, yet even those expeditions covered only limited ground. Most of the lake floor has never been observed directly by human eyes. Sonar provides outlines, but it cannot reveal the full complexity of biological communities or microtopography. There are trenches within the basins where sediment accumulates thickly. There are fault zones where rocks shift and crack. There are vent fields not yet fully catalogued. Part of the challenge lies in logistics. Lake Baikal's depth requires equipment capable of withstanding high pressure and extreme cold. Deploying submersibles or remotely operated vehicles demands significant funding and coordination. Weather conditions restrict seasonal access. In winter, ice cover complicates operations. In summer, storms can interrupt surface support. Each expedition must balance scientific objectives with practical constraints. Sediment drilling presents additional difficulty. Extracting cores from depths exceeding a kilometer requires stable platforms and specialized rigs. Ice-covered winters sometimes provide stability for drilling through ice, but extreme cold strains equipment. Sediment cores retrieved so far have provided remarkable records of climatic history, volcanic ash layers, and biological evolution. Yet these cores represent narrow cylinders in a vast basin. The full three-dimensional complexity of sediment deposition remains partially understood. Seismic reflection surveys have imaged subsurface structures, revealing folded layers and faulted zones beneath the sediment. These surveys show that the rift continues downward beyond what sediment cores can reach. Some models suggest that the total depth from surface water to the base of the rift may exceed 8 kilometers in places. That depth rivals some ocean trenches in vertical scale when considering the full geological structure, and still, drilling has penetrated only a fraction of that. The deepest scientific borehole in the Baikal region did not reach the base of the sediment column. Drilling deeper would require major international collaboration and resources comparable to ocean drilling programs. Why not drill all the way? Because the deeper you go, the more complex and expensive operations become. Drilling through kilometers of water and sediment risks destabilizing fragile structures. Equipment failure at such depths carries high cost. Moreover, scientific priorities must weigh benefits against risks. Some of the most intriguing unknowns involve microbial life deep within sediment layers. In ocean basins, researchers have discovered microbial communities living kilometers beneath the seafloor, metabolizing slowly in isolation for millions of years. Could similar communities exist beneath Baikal? Initial studies suggest the possibility. Samples from deeper sediment cores have revealed microbial DNA sequences not yet fully characterized. These microorganisms may survive on minimal energy, using chemical gradients produced by geothermal heat or organic matter buried long ago. Studying them could expand understanding of life's limits on Earth. It could also inform astrobiology, offering analogues for subsurface life on other planetary bodies. But accessing these communities requires deeper drilling and contamination-free sampling techniques. Even in areas where the lake floor has been visually documented, time-limited dives capture only snapshots. Ecosystems may vary seasonally or annually. Hydrothermal vent activity could fluctuate. Methane seep intensity may change. Without continuous monitoring at depth, long-term patterns remain partially inferred. Another layer of uncertainty involves tectonic processes below the sediment. Geophysical models indicate that crust beneath Baikal continues to thin and fracture, but the precise distribution of faults at depth is not fully resolved. Seismic networks record earthquake locations, yet the deeper mantle dynamics driving rifting remain topics of ongoing research. Is there a mantle plume beneath Baikal? Evidence for elevated heat flow suggests some thermal anomaly, but whether it constitutes a focused plume or broader lithospheric thinning remains debated. High-resolution seismic tomography could clarify mantle structure, but such studies require dense instrumentation arrays and years of data collection. The lake's remote location complicates large-scale deployments. Then there is methane. Methane hydrates have been identified within Baikal sediment. Mapping their distribution and stability under changing temperature conditions is crucial for understanding potential gas release scenarios. Hydrate deposits may extend unevenly across basins, influenced by sediment thickness, pressure, and geothermal gradient. Current data provide estimates, but not comprehensive maps. In ocean systems, methane hydrate destabilization can trigger submarine landslides. Could similar processes occur in Baikal? Large underwater landslides have been identified in sediment records, likely linked to earthquakes. Understanding the interaction between seismic activity and gas hydrates is an area still under investigation. The depths also conceal historical artifacts. During the Soviet era, various research projects operated on and around Baikal. Rumours persist about submerged equipment or experimental platforms. Most such stories are exaggerated, yet the lake's size and depth make it plausible that objects lost decades ago remain unrecovered. Recovery operations at extreme depth are costly and technically challenging. But the greater unknowns are biological and geological rather than archaeological. Every deep dive reveals organisms adapted to pressure and cold in ways that challenge expectations. Some amphipod species have been documented only once, captured in a single sampling event. Are they rare, or simply inhabiting regions not yet sampled? Species distribution models attempt to predict habitat zones based on depth, temperature, and substrate. Still, predictions must be tested by direct observation. The lake's depth also affects communication and data transmission. Signals attenuate quickly underwater. Cabled observatories, common in some ocean settings, are not yet widespread in Baikal. Deploying long-term sensor arrays at depth would enhance continuous monitoring, but funding and maintenance present obstacles. Climate change adds urgency. Surface warming trends may alter stratification patterns, potentially affecting deep oxygen transport. While deep waters remain oxygenated today, sustained changes in mixing could impact bottom communities. Monitoring requires baseline data. In a lake as large as Baikal, establishing comprehensive baselines takes time, and time is both Baikal's strength and its complication. Its geological and ecological processes unfold over millions of years. Human observation spans barely a century in scientific detail. We're studying an ancient system with relatively recent tools. Even satellite imagery, now routine, covers only the past few decades. Long-term change must be inferred by combining sediment records, historical accounts, and modern measurements. There is also the question of undiscovered species. Given the rate of new species identification in Baikal over the past decades, it is likely that additional endemic organisms remain undocumented. Deep zones, especially around vent fields or sediment slopes, may host niche communities not yet sampled. Molecular techniques such as environmental DNA sampling have begun to reveal hidden diversity. Water samples filtered and analysed for genetic fragments can detect organisms without physically capturing them. Early results suggest greater microbial diversity than previously catalogued. Expanding such surveys across basins could refine estimates. Still, even eDNA methods require strategic sampling locations, and with thousands of square kilometres of lake floor, complete coverage is a long-term endeavour. The phrase, "the depths we still haven't touched," also refers to conceptual depth. There are interactions within Baikal system not fully understood. How exactly does tectonic heat influence biological distribution? What are the feedback loops between methane seepage and microbial communities? How might gradual changes in ice cover alter deep water circulation over decades? Each question opens into sub-questions. Research in Baikal often proceeds incrementally. One expedition measures temperature gradients, another analyses plankton shifts, another maps sediment chemistry. Together, these efforts build a composite picture. Yet gaps remain. Part of what makes Baikal compelling to scientists is precisely this incompleteness. Unlike many ecosystems heavily modified or mapped exhaustively, Baikal retains elements of mystery, not because it is hidden by myth, but because it is vast and technically demanding. Standing on the shore, looking across its surface, it is difficult to imagine how much remains unseen below. The water appears calm, reflective. Boats cross without sensing the vertical distance beneath them. Ice in winter conceals depth under a frozen plain, yet below, pressure, cold, microbial metabolism, tectonic strain, and sediment accumulation continue quietly. There is no dramatic chasm glowing red, no monstrous forms lurking in darkness. What remains untouched is subtler. It is the cumulative complexity of a rift basin that has evolved for tens of millions of years and still shifts millimetre by millimetre each year. It is the unseen microbial networks metabolizing buried organic matter. It is the distribution of methane hydrates and the long-term implications of their stability. It is the precise architecture of faults beneath kilometers of sediment. It is the seasonal variability of deep benthic communities. Science thrives on questions. Baikal offers them in abundance, touched points on the map. We have sampled the lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The lake's geological history spans epochs. We have 1,000 meters of data. The touched points on the map. We have sampled cores from selected coordinates. We have recorded seismic waves passing through crust. But the totality of Baikal's depths remains beyond complete grasp. And that is not a failure of science. It is a reflection of proportion. When the deepest freshwater lake on Earth sits atop an active continental rift, holding sediments that record climate over millions of years and ecosystems found nowhere else, it will not yield all its information easily. It will require patience equal to its age. And as researchers continue descending, drilling, sampling and modelling, they remain aware that beneath the measured depths lie layers and processes still unfolding, still inaccessible in full, reminding us that even in an age of satellites and submersibles, Some parts of the world remain only partially known. When scientists lower a drill through more than a kilometer of water into the floor of Lake Baikal, they are not simply collecting mud, they are extracting time. Layer by layer, millimeter by millimeter, sediment has settled at the bottom of the lake for tens of millions of years. Each grain of silt, each microscopic shell, each trace of volcanic ash represents a moment in Earth's environmental history. Most lakes cannot offer that kind of record. They dry up. They fill with sediment too quickly. They are scoured clean by advancing glaciers. Their histories are interrupted. Baikal's basin continued to deepen as sediment accumulated. That rare balance between filling and subsiding allowed a nearly continuous archive to form. Some sediment cores retrieved from Baikal extend back more than 5 million years without major interruption. Seismic data suggests that deeper layers could record up to 25 million years of environmental change. That span covers dramatic shifts in global climate. When Baikal first formed, Earth was warmer. There were no polar ice caps as we know them today. Over time, global temperatures declined. Ice sheets expanded and retreated. Atmospheric carbon dioxide fluctuated. Each of those changes left traces in Baikal's sediment. Diatoms are central to this archive. Diatoms are microscopic algae encased in silica shells. Different species prefer different environmental conditions. Some thrive in colder water, others in warmer. Some indicate high nutrient availability, others suggest low productivity. When diatoms die, their silica shells sink and become part of the sediment. By analysing the species composition in each sediment layer, scientists reconstruct past water temperatures, nutrient levels, and seasonal patterns. In Baikal, many diatom species are endemic. Their evolutionary history is intertwined with the lake itself. That makes interpretation complex but also rich. Changes in diatom communities over time reflect both global climate shifts and local evolutionary responses. In addition to biological remains, sediment contains chemical signatures. Isotopes of oxygen and carbon embedded in diatom shells and organic material provide clues about past temperatures and atmospheric composition. The ratio of oxygen 18 to oxygen 16, for example, varies depending on temperature and evaporation rates. By measuring isotopic ratios in successive layers, scientists can estimate how regional climate evolved. Baikal's archive includes evidence of ice ages. During colder periods, glacial expansion influenced wind patterns and dust deposition. Sediment layers from these times often show increased mineral content, indicating greater erosion in surrounding mountains. Warmer interglacial periods leave different markers, such as higher organic content reflecting stronger biological productivity. Because the lake's water has long residence time, approximately 330 years on average, changes in inflow and precipitation are recorded gradually but persistently. River discharge from the Selenga and other tributaries reflects precipitation patterns in vast areas of Siberia and Mongolia. When monsoon systems strengthen or weaken, sediment composition changes. Volcanic eruptions also leave distinct signatures. Thin layers of ash can be identified and chemically matched to known eruptions in Asia and beyond. These ash layers serve as time markers, helping align Baikal's sediment record with global geological timelines. One of the most significant drilling projects in Baikal occurred in the 1990s and early 2000s, involving international collaboration. Researchers extracted long cores that revealed uninterrupted records of environmental change. The data from those cores contributed to global paleoclimate reconstructions. Baikal's archive is particularly valuable because it represents a continental interior. Many long climate records come from ocean sediments or polar ice cores. Ocean cores reflect global patterns influenced by marine circulation. Ice cores capture atmospheric composition directly, but are limited to glaciated regions. Baikal offers a terrestrial perspective from mid-latitude Asia. This region plays a crucial role in global climate systems. It influences and is influenced by the Asian monsoon, Siberian high-pressure systems, and Arctic oscillations. Understanding how these systems behaved millions of years ago helps scientists refine climate models. The depth of sediment beneath Baikal is extraordinary. Seismic surveys estimate sediment thickness exceeding 7 kilometers in some basins. Not all of that thickness has been sampled. Drilling through kilometers of sediment beneath a kilometer of water is technically demanding. So far, cores have penetrated only a fraction of total sediment depth, yet even that fraction spans millions of years. In some segments, sedimentation rates are relatively high, allowing high-resolution analysis. A centimetre of sediment might represent decades or centuries depending on location. In deeper, more stable zones, resolution can reach annual layers under certain conditions. Seasonal variations in diatom deposition sometimes create varves, annual laminations similar to tree rings. Counting these layers provides precise chronologies for recent millennia. Further down, layers compress and resolution decreases, but the overall sequence remains intact. What makes Baikal's record so powerful is its continuity. Unlike many continental lakes disrupted by glaciation, Baikal's depth shielded it from complete freezing or scouring during ice ages. Surface ice formed, but the basin persisted. Life continued in deeper waters. Sediment accumulated steadily. This continuity allows comparison across multiple glacial-interglacial cycles. Scientists can observe how ecosystems responded to repeated warming and cooling phases. Did plankton communities collapse during extreme cold? Did oxygen levels at depth fluctuate significantly? How did river inflow change with shifting precipitation patterns? These questions are addressed layer by layer. Baikal's sediment also captures evidence of tectonic pulses. Periods of accelerated rifting may have altered basin depth and sedimentation patterns. Shifts in grain size distribution sometimes correspond with seismic events or uplift episodes in surrounding mountains. Thus, the archive records both climate and geological change. There is also interest in methane hydrates within sediment layers. Changes in sediment temperature over geological time influence hydrate stability. By analysing hydrate distribution in relation to past climate phases, researchers can estimate how warming events affected methane storage. This has implications for understanding future methane release under global warming scenarios. One reason Baikal's archive unsettles some scientists is its contrast with modern trends. Sediment layers show natural climate variability across millions of years. Temperature fluctuations occurred gradually compared to current rates. Modern warming appears rapid when placed against that backdrop. By comparing isotopic data from recent sediment with deep historical layers, scientists quantify how unusual present trends may be. In some analyses, recent decades show shifts in diatom composition and isotopic signatures, consistent with warming beyond the range of variability observed in certain previous cycles. Interpreting these findings requires caution. Natural variability exists, but the speed of modern change stands out. There are also human signals in recent sediment layers. Industrial pollutants such as heavy metals and synthetic compounds appear in upper strata. These markers provide a timeline of anthropogenic influence. Even remote Baikal reflects global industrialization in its most recent layers. Lead isotopes from fuel combustion, traces of persistent organic pollutants, and microplastics have been detected. These contaminants form a thin but distinct cap atop millions of years of natural deposition. Future geologists, millions of years from now, would see this layer as a boundary, an abrupt chemical shift marking human presence. That realization carries weight. Baikal's archive demonstrates that Earth's climate has changed many times. It also shows that ecosystems adapt over long periods, but it underscores how quickly new signatures can appear. The sediment record is not static. It continues to grow. Every year, new material settles. Every storm, every bloom, every volcanic eruption, every river surge contributes. In the coming decades, continued warming, altered precipitation, and human activity will imprint additional signals. Scientists working with Baikal cores must account for compaction. As sediment accumulates, lower layers compress under pressure. Chemical processes alter original material over time. Advanced techniques such as radiometric dating, magnetic stratigraphy, and molecular biomarkers help refine interpretations. Collaboration across disciplines is essential. Geologists, chemists, biologists, and climate modelers work together to extract meaning from layers. The value of this archive extends beyond regional interest. Global climate models rely on accurate reconstructions of past conditions. Data from Baikal feed into international databases. Comparisons with marine cores and polar ice records improve understanding of hemispheric climate synchronization. For example, correlations between Baikal sediment isotopes and Greenland ice core data reveal links between mid-latitude Asian climate and North Atlantic temperature shifts. Such connections illustrate the interconnectedness of Earth systems. There are still deeper layers unexamined. If drilling technology advances and funding aligns, future projects may penetrate further into the sediment column. What might those deeper layers reveal? Perhaps transitions marking the initial formation of the lake. Perhaps evidence of earlier climate regimes predating current reconstructions. Each additional meter downward represents thousands or millions of years. The archive extends beyond the reach of current drills. Accumulate, recording changes in monsoons, rocky shores, perhaps drifting ice. Beneath layers accumulate, recording changes in monsoons, volcanic eruptions, glacial cycles, and human industry. This layered memory distinguishes Baikal from most freshwater bodies. It is not only deep in water, it is deep in time, and as scientists continue to analyze samples, refine dating techniques, and integrate data into broader climate frameworks, the lake continues to function as one of the longest continuous continental climate archives on Earth. Its sediment holds stories stretching back to epochs when continents were arranged differently, and mammals looked unfamiliar. Those stories are not finished, they extend upward into the present, and the rate at which new layers form now may one day stand out as sharply as volcanic ash bands or glacial dust deposits, marking a period when a species capable of drilling into ancient mud began leaving its own unmistakable trace in one of the deepest freshwater basins on the planet. When people think of earthquakes, they usually imagine buildings shaking, windows rattling, streets cracking open. The image is urban, immediate, loud. Lake Baikal changes that image. Here, earthquakes happen under more than a kilometer of water. The ground shifts beneath sediment, beneath pressure, beneath darkness. There are no collapsing skyscrapers in the middle of the lake, no sirens echoing across open water. And yet, the tectonic forces at work beneath Baikal are very real. Because the lake sits directly inside an active continental rift zone, earthquakes are not rare anomalies, they are part of the system. The Baikal Rift Zone is one of the most active intracontinental rifts on Earth. While it does not produce earthquakes as frequently or as powerfully as major plate boundaries like the Pacific Ring of Fire, it consistently generates seismic activity. Some of these quakes occur on land around the lake, others occur directly beneath the lakebed. Seismographs installed around Baikal record hundreds of small earthquakes every year. Most are minor, too weak to be felt by people living nearby, but occasionally stronger events occur. In 1862, a significant earthquake caused a dramatic change in the landscape near the Selenga River Delta. A section of land subsided and flooded, forming what is now known as Proval Bay. That was not beneath the deepest part of the lake, but it demonstrated how rift activity can reshape the region quickly. More recently, in 1959, a magnitude 6.8 earthquake struck near Baikal. The epicenter was close to the southern basin. Though damage was limited due to sparse population, the event confirmed that substantial energy can be released within the rift system. Underwater earthquakes behave differently from those on land. The shaking travels through rock, then into sediment, then into water. Water does not transmit shear waves the same way solid ground does. Instead, pressure waves propagate outward, In deeper sections of the lake, sediment layers can amplify or dampen motion depending on their composition. Seismic surveys show that Baikal's sediment is not uniform. Some areas consist of fine-grained, loosely compacted material. Others contain denser layers deposited during different climatic phases. When an earthquake occurs beneath such layers, the response varies. In certain cases, shaking can trigger underwater landslides. These are not cinematic avalanches plunging dramatically into abyssal trenches. They are more often gradual slumps of sediment shifting downslope. But even gradual movement can redistribute large volumes of material. Sediment cores from Baikal sometimes contain distinct disturbed layers, chaotic deposits sandwiched between more orderly sediment. These layers are interpreted as evidence of past seismic-triggered landslides. Each disturbed layer marks a moment when the lake floor shifted. These underwater landslides can also release trapped methane. As sediment moves, pressure conditions change. Methane hydrates, which form under stable low-temperature, high-pressure conditions, may destabilize locally. Released gas forms bubbles that rise through the water column. Most methane dissolves before reaching the surface, but the process reflects the interconnectedness of tectonics and chemistry. Earthquakes also influence hydrothermal systems. Fault lines act as conduits for heated water from deeper crustal levels. When faults slip, permeability can change. New fractures may open, allowing increased flow of warm, mineral-rich water. Existing pathways may close. Monitoring of hydrothermal vent sites sometimes reveals subtle changes following seismic events. The lake floor is not flat and static. It is structured by normal faults typical of rift environments. These faults create steep escarpments and tilted blocks beneath the water. High-resolution sonar mapping shows scarps where one block of crust is dropped relative to another. Some of these scarps extend for tens of kilometers. When slip occurs along these faults, even by a few centimeters, it releases accumulated stress built up over years or decades. Most underwater earthquakes in Baikal are moderate in magnitude. They rarely generate large tsunamis because the enclosed nature of the lake and the geometry of fault movement limit vertical displacement of water. However, localized waves can occur, particularly if a landslide displaces water suddenly. Historical records describe unusual wave activity following certain seismic events, though not at catastrophic scale. Because the lake is long and narrow, wave energy tends to travel along its length rather than dispersing outward uniformly. The depth of Baikal affects how seismic energy interacts with water. In shallower lakes, bottom motion can directly agitate the entire water column. In Baikal, extreme depth means that energy dissipates before reaching the surface in many cases. Yet sensitive instruments detect subtle disturbances. Modern seismology in the Baikal region relies on a network of stations placed both onshore and near the lake. These instruments record ground motion continuously. By analysing wave arrival times, scientists determine earthquake locations and depths. Data show that seismicity clusters along specific fault segments. The central basin, being deepest, corresponds with zones of significant crustal thinning. It is not surprising that many earthquakes originate beneath this basin. Seismic tomography studies aim to image the crust and upper mantle beneath Baikal. These studies analyse how seismic waves travel through different materials. Slower wave speeds may indicate hotter or partially molten regions. Some results suggest elevated temperatures beneath the rift, supporting the idea that thermal processes contribute to crustal weakening. Is there active magma beneath Baikal? Evidence does not point to large magma chambers similar to those beneath volcanoes. However, the presence of volcanic rocks in surrounding regions indicates past magmatic activity. Heat flow measurements in parts of the lake are higher than average continental values. This suggests that the mantle beneath Baikal may be warmer or thinner than surrounding areas. Warmth at depth reduces rock strength. Reduced strength allows continued extension. Continued extension generates earthquakes. This cycle persists quietly. For residents along the shore, most earthquakes are minor tremors felt as brief vibrations. Buildings sway slightly. Objects rattle. For those on the lake itself, particularly during winter when ice covers the surface, seismic events can produce unusual sensations. Ice amplifies certain vibrations. Cracks may propagate suddenly following a tremor. Sound travels rapidly across the frozen surface. A quake that might feel mild on land can echo dramatically across ice. There have been instances where winter travellers reported hearing loud cracking sounds shortly after feeling shaking. It is not the ice causing the earthquake, it is the ice responding to it. Earthquakes beneath Baikal are reminders that the lake's formation process continues. The rift has not completed its work. GPS measurements confirm that the crust around the lake continues to widen by a few millimetres per year. That movement accumulates stress along faults. Eventually that stress releases as earthquakes. The pattern is not random. Over geological time, rift systems often experience episodic intensification. Periods of relative calm may be punctuated by phases of increased seismicity. Sediment records can capture evidence of such phases through disturbed layers and shifts in deposition rates. Scientists analyse these patterns to understand long-term rift evolution. There is also interest in how climate interacts with seismic activity. Changes in lake level alter pressure on the crust. Although the mass of water is small relative to tectonic forces, significant fluctuations over geological timescales could influence stress distribution. For example, during glacial periods when precipitation patterns shifted, lake levels may have varied. These variations might have modulated fault activity slightly. Such feedbacks are complex and remain under study. From a risk perspective, Baikal's underwater earthquakes pose limited direct threat compared to major tectonic boundaries. Population density around the lake is relatively low. Infrastructure is modest compared to large metropolitan regions. Still, understanding seismic behaviour remains important for regional planning and safety. More broadly, Baikal provides a rare opportunity to study intracontinental rifting in progress. Unlike oceanic spreading centres hidden beneath kilometres of seawater, Baikal's rift is accessible from land. Scientists can combine terrestrial and underwater observations. They can correlate sediment records with seismic data. They can monitor crustal movement with GPS. Few places offer such a comprehensive natural laboratory. There is a quiet tension in knowing that beneath calm, reflective water lies a crust under strain. A strain that built the deepest freshwater lake on Earth. A strain that continues to shape its basins. Most days, Baikal appears serene. Waves ripple gently across its surface. Ice forms clean, geometric sheets in winter. Tourists walk along rocky shores, but beneath that surface faults extend downward into thinning crust. Pressure accumulates slowly, then releases. The release may be subtle, a minor tremor recorded only by instruments, or it may be strong enough to be felt across villages along the shore. Each earthquake is a reminder that the lake is not static. It is part of a geological process still unfolding. And while underwater earthquakes rarely produce dramatic spectacle visible from above, they contribute incrementally to the shape, depth, and chemistry of the basin. They influence sediment stability. They alter hydrothermal flow. They adjust stress fields. They keep the rift alive. In the context of millions of years, these events are small adjustments. In human terms, they are sudden and noticeable. Together they form the rhythm of a continent slowly separating beneath a body of water so deep that most of its movements remain unseen, except by instruments listening carefully to vibrations travelling through rock, sediment and cold fresh water in the dark. Far below the surface of Lake Baikal, beneath more than a kilometre of cold, oxygen-rich water, and beneath thick layers of sediment accumulated over millions of years, something invisible is stored under pressure. Methane. Not in vast explosive chambers waiting to erupt without warning, but trapped quietly in ice-like structures called methane hydrates. Methane hydrate forms when methane molecules become encased within crystalline cages of water under conditions of high pressure and low temperature. These conditions are common in deep ocean sediments. They are much less common in freshwater systems, and yet Baikal has them. The combination of extreme depth and cold bottom temperatures creates a stability zone where methane hydrates can persist. Pressure at the deepest point of Baikal exceeds 160 atmospheres. Temperatures at the lake floor hover just above freezing. Under these conditions, methane released from decomposing organic matter or geological processes can become trapped within hydrate structures. The presence of methane hydrates in a continental rift lake is unusual enough to attract significant scientific attention. Methane itself is not rare. It forms naturally when organic material decomposes in low oxygen environments. In lakes and wetlands around the world, methane is produced by microbial activity in sediments. What makes Baikal different is scale and storage mechanism. Because sediment beneath Baikal is thick, several kilometers in some areas, organic material has been buried and compressed over immense spans of time. Microbial processes continue at depth, breaking down this material and releasing methane. Under sufficient pressure, that methane becomes incorporated into hydrates rather than escaping immediately. Hydrates are stable only within specific pressure and temperature ranges. If pressure drops or temperature rises beyond certain thresholds, the hydrate structure destabilizes. Methane is released as gas. Scientists have identified methane seeps in Baikal, locations where gas bubbles rise from the lake floor through the water column. Submersible observations have documented streams of bubbles emerging from fissures in sediment. In winter, when the surface freezes, some of these bubbles become trapped beneath the ice. Over time, successive releases create stacked columns of frozen bubbles visible through clear ice. These formations have become visually iconic, but they are also data. Each bubble represents methane that escaped hydrate or sediment. Most of this methane dissolves in water before reaching the atmosphere. Microorganisms in the water column oxidize methane, converting it into carbon dioxide. This microbial oxidation acts as a biological filter, limiting atmospheric release. Still, the presence of methane hydrates in Baikal raises important questions. How stable are these hydrates under current climate trends? If surface temperatures rise and mixing patterns change, could bottom water temperatures shift enough to affect hydrate stability? Current measurements suggest that deep water in Baikal remains remarkably stable in temperature. Even as surface waters warm seasonally, bottom temperatures fluctuate minimally. That stability provides reassurance. However, long-term warming could influence deep circulation patterns. If vertical mixing changes, temperature gradients might adjust. Hydrate stability zones are sensitive to even small thermal shifts over time. In ocean settings, researchers have expressed concern that warming seawater could destabilize methane hydrates along continental margins, potentially releasing significant greenhouse gases. Baikal's hydrate deposits are smaller in total volume compared to global ocean reserves. Even so, they are significant within a freshwater context. Estimating total methane stored beneath Baikal remains challenging. Hydrate distribution is not uniform. Seismic reflection surveys can detect indicators of hydrate presence, such as bottom simulating reflectors, acoustic signatures marking boundaries between hydrate-bearing sediment and free gas zones. Several such features have been identified in Baikal basins. Core samples have confirmed hydrate presence in certain locations, yet mapping the full extent of hydrate deposits requires more data. There is also the interaction between methane and tectonics. Because Baikal lies within an active rift, fault movement can influence gas migration. Earthquakes may fracture sediment layers, allowing methane to escape from deeper zones. Underwater landslides triggered by seismic activity can disturb hydrate stability locally. Each tectonic adjustment potentially alters methane pathways. Hydrothermal activity may also play a role. Warmer water rising along faults can influence local temperature conditions, potentially affecting hydrate formation or dissociation in nearby sediment. These processes are not explosive in the dramatic sense sometimes portrayed in popular media. They are gradual, episodic, and localized. Yet their cumulative effect shapes the chemical environment of the lake. Methane is more than a greenhouse gas. Within the lake, it fuels microbial ecosystems. Certain bacteria oxidize methane as an energy source. Around methane seeps, microbial mats have been observed. These communities form at the interface between oxygen-rich water and methane-rich sediment. Studying them helps scientists understand how life exploits chemical gradients in extreme environments. There are parallels with deep-sea methane seep ecosystems. In oceans, methane seeps support specialized communities including clams and tube worms. In Baikal, analogous large organisms are absent, but microbial diversity near seeps is notable. The methane cycle within Baikal is a closed system to a large extent. Methane produced in sediment either becomes trapped in hydrate, oxidized by microbes, or eventually released to the atmosphere in small amounts. The balance between these pathways depends on temperature, pressure, microbial activity, and tectonic disturbance. Monitoring methane flux is therefore part of broader ecological study. Researchers deploy underwater sensors to measure gas concentrations. Winter ice provides opportunities to capture gas samples directly from trapped bubbles. Chemical analysis of these bubbles reveals isotopic signatures that distinguish between microbial methane and thermogenic methane. Gas formed deeper in the crust through geological processes. In Baikal, both sources appear to contribute. Microbial methane dominates in many shallow sediment zones. Thermogenic methane may originate deeper within the rift structure. The presence of thermogenic methane reinforces the idea that Baikal's rift remains geologically active. Heat and pressure conditions at depth support hydrocarbon formation. The quantities involved are modest compared to major oil and gas basins. Still, their existence highlights the complexity beneath the lake. Climate scientists pay attention to methane because of its potency as a greenhouse gas. Over a 20-year timescale, methane has a much stronger warming effect than carbon dioxide. Even small releases can influence atmospheric chemistry locally. However, current evidence suggests that Baikal's methane emissions to the atmosphere are limited. Most methane released from sediment dissolves in the water column and is consumed by microbes before reaching the surface. Winter ice cover further restricts direct emission for part of the year. As ice melts in spring, some accumulated methane may escape, but measured fluxes remain relatively small compared to global methane sources such as wetlands and agriculture. The concern is not immediate catastrophe, it is sensitivity. A system that has stored methane stably for thousands or millions of years under cold, high-pressure conditions may respond to gradual warming in ways not fully predictable. Long-term datasets are necessary to track trends. Methane seeps have been documented in multiple basins of Baikal. Some appear persistent, releasing gas continuously at low rates. Others may be episodic, activated by seismic events or sediment shifts. Mapping these seeps requires repeated surveys. High-resolution sonar can detect bubble plumes rising through the water column. Visual confirmation from submersibles provides additional detail. In some dives, researchers observed clusters of bubble streams emerging from small areas. Sediment around these sites sometimes appears disturbed or fractured. Such observations link methane release with tectonic and sedimentary dynamics. There is also interest in how methane hydrates contribute to sediment stability. Hydrates can cement sediment grains together, increasing mechanical strength. If hydrates dissociate, sediment may weaken. In marine settings, hydrate destabilization has been linked to submarine landslides. In Baikal, similar processes are theoretically possible, though large-scale slope failures are rare. Understanding sediment mechanics under hydrate influence is part of ongoing research. From a broader perspective, methane from the deep adds another layer to Baikal's uniqueness. Few freshwater lakes combine extreme depth, active tectonics, hydrothermal systems, endemic biodiversity, and methane hydrates in a single basin. Each component interacts with the others. Tectonics influence heat flow. Heat flow affects hydrate stability. Hydrate stability shapes methane release. Methane release fuels microbial communities. Microbial activity influences chemical balance. Chemical balance affects ecosystem health. It is a network rather than an isolated phenomenon. From the surface, none of this is visible. Visitors see clear water stretching to the horizon. In winter, they see frozen expanses dotted with trapped bubbles. Those bubbles are often photographed for their beauty. Less visible is the slow geological process beneath them. Methane does not roar out of Baikal in violent bursts. It seeps quietly. It accumulates gradually. It is filtered by microbes. It freezes into columns beneath ice. It dissolves into water. It reflects pressure and time. Scientists continue to monitor temperature profiles, seismic activity, and gas flux. They model hydrate stability under projected warming scenarios. They compare Baikal's methane dynamics with marine systems. They refine understanding of how continental rifts interact with carbon cycles. Methane from the deep is not a dramatic villain in Baikal's story. It is a component of a system that has evolved over tens of millions of years. Yet it serves as a reminder that beneath the calm, transparent surface lies chemistry influenced by tectonic strain and ancient organic matter. And in a world where atmospheric composition is changing rapidly, even quiet reservoirs of methane are part of a larger conversation about stability, feedback, and the long memory of Earth's carbon cycle locked within one of its oldest freshwater basins. There is a word that appears again and again in field notes, travel accounts, and even in private conversations between researchers who have spent time on Lake Baikal: alien. Not in the sense of spacecraft or visitors from another planet, not in a way that suggests science fiction. Alien in the sense of unfamiliar, out of place, difficult to compare to anything else on Earth. It begins with scale. Baikal does not behave like most lakes. It stretches more than 600 kilometers from north to south. In certain places, the opposite shore disappears beyond the curve of the horizon. When you stand at the water's edge, you're not looking across a pond or even a typical inland sea. You're looking at a body of water that contains more liquid fresh water than all the Great Lakes of North America combined. And yet it is not an ocean. The water is fresh. The waves are shaped by wind but lack the salt tang of the sea. There are no tides in the oceanic sense. This contradiction alone creates a subtle disorientation. Then there is the clarity. Water that transparent, that deep, does not align with most people's expectations. Looking down through dozens of meters of water into darkness feels less like observing a lake and more like peering into space. In shallow lakes, murkiness limits vision. In Baikal, visibility can be so high that depth becomes harder to judge. The mind struggles to calculate distance through water that seems almost absent. Divers describe descending in Baikal as entering a vertical landscape rather than submerging in a body of water. At several hundred meters, sunlight fades completely. Below that, the environment is cold, stable, and black. Pressure increases steadily. Temperature hovers near freezing year-round. These conditions resemble deep ocean environments more than inland freshwater systems. Yet above, snow-covered mountains frame the horizon. You're in Siberia, surrounded by forest and steppe, standing above an abyss more commonly associated with ocean trenches. The geology contributes to the feeling. Baikal sits within a continental rift that continues to widen slowly. The ground beneath is not settled. Faults cut through crust below the lake. Earthquakes occur regularly. Standing on the shore, the land feels solid. Knowing that the crust beneath is under tension alters perception. The lake is not simply resting in a depression. It occupies an active fracture in a continent. In winter, the alien sensation intensifies. The surface freezes into a sheet of clear blue ice, stretching for hundreds of kilometers. Cracks form in geometric patterns. Methane bubbles freeze into vertical columns. Pressure ridges rise unexpectedly from flat expanses. Walking across that ice feels less like crossing a frozen lake, and more like traversing a glass plane suspended above darkness. Sound carries differently. Deep booms echo across the surface as ice expands and contracts. The lake groans under temperature shifts. At night, under clear skies, the frozen surface reflects stars so sharply that horizon lines blur. It becomes difficult to orient yourself. There are few artificial lights in many areas around Baikal. The surrounding region remains sparsely populated. The absence of light pollution reveals a night sky dense with stars. Reflected in ice, the sky appears doubled. It's easy to understand why early explorers described the lake in language that bordered on metaphysical. But there is nothing supernatural about it. It is the product of physics and geography. The biodiversity adds another layer. More than half of the species in Baikal exist nowhere else. Amphipods adapted to pressure and cold move across the lake floor. Translucent golomyanka fish inhabit mid-water depths. A freshwater seal breeds on ice in the middle of a continent. The presence of a seal in a lake thousands of kilometers from the ocean disrupts intuitive expectations. The lake does not fit neatly into ecological categories. It is freshwater, yet ocean-like in depth and certain chemical features. It is ancient yet geologically active. It is isolated yet globally significant in climate research. This combination challenges classification. Scientists often rely on comparisons to understand new systems. Baikal resists easy comparison. It is not quite like Lake Tanganyika, though both are deep rift lakes. It is not quite like the Caspian Sea, though both are large inland water bodies. It is not quite like an ocean trench, though its depth invites such parallels. It occupies a category that is largely its own. The feeling of alienness also arises from time. Baikal is approximately 25 million years old, far older than most lakes on Earth. Most freshwater bodies are ephemeral on geological scales. They form and disappear with glacial cycles. Baikal persisted. It deepened gradually as sediment accumulated. Its ecosystems evolved continuously within that basin. Standing on its shore, you are looking at water that overlies sediment recording climate shifts long before humans existed. You're looking at a system that was already ancient when the first hominins walked in Africa. Time accumulates differently here. There is a sense that processes unfold slowly and steadily beneath the surface, indifferent to human presence. Even modern infrastructure feels small against that backdrop. Small towns line portions of the shore. Research stations dot certain areas. But vast stretches remain undeveloped. Wind moves across open water for kilometers without interruption. Storms build quickly and dissipate just as fast. Weather patterns shift abruptly in transitional seasons. The lake generates its own microclimates. Fog can form suddenly when cold air meets relatively warmer water. In summer, the surface may appear calm while deeper currents move quietly below. There is also a psychological element tied to remoteness. Southern Siberia is not easily accessible for many people. Travel to Baikal often involves long journeys across rail lines or flights into regional airports. The distance from major global cities contributes to the impression of entering a different environment. Even experienced field researchers sometimes describe the first days on Baikal as disorienting. Not because of danger, but because scale and clarity and silence combine in ways that are uncommon elsewhere. In many natural environments, there are constant background sounds, traffic in the distance, aircraft overhead, industrial hum. In remote parts of Baikal's shoreline, wind and water dominate. In winter, snow absorbs sound. Ice transmits it differently. Silence feels amplified. Then there are the circles in the ice visible from satellites. Large, near-perfect rings formed by subsurface convection currents. They look artificial in photographs, yet they are natural expressions of water and heat interacting beneath frozen surface. Seeing such geometric shapes in a landscape otherwise defined by organic forms adds to the sense of strangeness. Hydrothermal vents beneath a freshwater lake also defy common expectation. Warm mineral-rich water rising from fractures in cold sediment seems more appropriate to mid-ocean ridges. In Baikal, these vents are smaller but real. They support microbial communities adapted to chemical energy rather than sunlight. Few people imagine hydrothermal systems when they think of lakes, and yet they are there. The alien feeling is not about fear, it is about unfamiliar combinations. Depth usually implies salt water, seals usually imply coasts, hydrothermal vents usually imply oceans, methane hydrates usually imply continental margins. In Baikal, these features converge within a single inland basin. Even the colour of the water can appear different depending on season and light. In summer, it can shift from deep blue to turquoise. In winter, ice may appear sapphire or pale green depending on thickness and angle of sun. Transparency enhances these variations. Photographs often struggle to capture the exact hue because it changes with perspective. Scientists working in Baikal often adapt equipment designed for marine environments because freshwater systems of this scale are rare. Submersibles built for ocean research have been deployed there. Instruments calibrated for seawater chemistry must be adjusted for freshwater conditions. This blending of marine and freshwater research practices underscores Baikal's hybrid nature. It is a lake, but it does not behave like most lakes. The alien sensation may also reflect human expectations more than the lake itself. We categorize environments into familiar types. When something does not align with those categories, it feels foreign. Baikal does not align neatly. It is too deep, too old, too active, too isolated, and too biodiverse for a typical freshwater body. At the same time, it is not boundless like the ocean. Its shores are visible in some places. Its boundaries are defined. This tension between contained and immense creates cognitive dissonance. Even climate records extracted from its sediment reveal shifts across millions of years. Reading those data while standing at the water's edge can feel like observing two timescales simultaneously. Immediate wind across the surface, ancient climate transitions compressed beneath. The alien quality is therefore layered. It is sensory, clarity, sound, ice, depth. It is geological, rifting crust, hydrothermal heat. It is biological, endemic species, freshwater seal. It is temporal, millions of years recorded in mud. It is spatial, a near-oceanic body enclosed within a continent. None of these elements alone would create that impression. Together, they do. And perhaps that is why scientists often return to Baikal not only for data, but for perspective. Because standing beside a lake that challenges categories forces reconsideration of assumptions about how Earth systems are organized. It demonstrates that continental interiors can host abyssal depths, that fresh water can sustain ocean-like processes, that isolation can generate biodiversity rivaling islands and reefs. The alien feeling does not signal danger, it signals rarity. It signals a combination of forces and histories unlikely to be repeated elsewhere in exactly the same way. And in a world where many landscapes feel increasingly mapped, quantified, and familiar, Baikal retains an atmosphere of difference, not because it hides secrets of fantasy, but because it embodies geological and ecological intersections that remain uncommon on this planet, reminding observers that even on Earth, some environments feel as though they belong to a category of their own. Long before sediment cores were drilled, before seismic stations were installed along the shoreline, before satellites traced circles in winter ice, people stood at the edge of Lake Baikal and tried to explain what they were looking at. They did not have bathymetric maps. They did not know the lake was more than 1,600 meters deep. They did not speak in terms of tectonic rifts or methane hydrates. What they had was observation, memory, and imagination, shaped by a landscape that already felt different. Among the indigenous Buryat people, whose communities have lived around Baikal for centuries, the lake is not just water. It is sacred. It is often referred to as a sea rather than a lake, reflecting both its scale and its power. In the Buryat language, Baikal is called Dalai Nor, meaning sacred sea. The word sea is not used casually. For people living without modern instruments, The lake's size and behaviour justified that classification. Waves could rise suddenly during storms, wind could change direction quickly, boats could disappear beyond the horizon. To early inhabitants, this was not a pond contained within familiar limits. It was a vast, unpredictable body. Many Buryat legends describe Baikal as an ancient father figure, stern and powerful. In some stories, he has many daughters, represented by rivers flowing into him. The Angara River, the only river flowing out of Baikal, is often portrayed as a rebellious daughter who fled to join the Yenisei River. One legend tells that Baikal, angered by Angara's departure, threw a large rock after her. That rock, known today as the Shaman Rock near the mouth of the Angara River, still protrudes from the water. From a geological perspective, Shaman Rock is simply a remnant of resistant bedrock. From a cultural perspective, it is part of a narrative explaining the lake's hydrology. The lake's depth also gave rise to stories. Without instruments, no one could measure it precisely. Fishermen lowered weighted lines and felt them descend far beyond expected lengths. Some accounts claimed that the lake had no bottom. Others suggested that it connected through underground passages to distant seas. In many cultures, extreme depth invites myth. It suggests hidden worlds. In Baikal's case, the idea of bottomless water persisted for generations. Even when modern measurements confirmed a maximum depth, the sense of immeasurable vastness remained in cultural memory. Storms contributed to legend as well. Baikal is known for sudden, powerful winds. The Sama wind, for example, can descend rapidly from surrounding mountains, reaching speeds strong enough to overturn small boats. Before meteorology, such winds were interpreted as manifestations of spirits or moods of the lake. Sama itself appears in folklore as a force with intention. When wind rises abruptly and waves crash against shore, it is easy to attribute agency. Winter ice inspired its own stories. The groaning sounds, the booming cracks, the shifting pressure ridges, all of these were heard long before scientists explained thermal expansion and contraction. To those living near the lake, these sounds were voices. In some tales, the ice spoke warnings. In others, it expressed the lake's displeasure. Even today, locals sometimes speak of listening carefully to ice sounds before venturing onto it. Not because they believe in spirits inhabiting cracks, but because generations learned that sound carries information about stability. Folklore and practical knowledge often blend. The Buryat shamanic tradition holds Baikal as a place of spiritual significance. Shaman Rock, mentioned earlier, was historically a site for rituals. Offerings were made to ensure safe travel across the lake or successful fishing. Travellers tied ribbons to trees near the shore as gestures of respect. These practices reflected recognition of the lake's power. The lake gives fish, water and transportation. It can also take lives. Boats have capsized in sudden storms. Ice has broken unexpectedly beneath travellers. Legends often preserve cautionary lessons. Stories of water spirits pulling careless individuals beneath the surface may have functioned as warnings about respecting the lake's unpredictability. There are also accounts of a creature said to inhabit Baikal's depths. In some regional folklore, fishermen spoke of a large serpentine animal, glimpsed briefly near the surface, or seen as a shadow beneath boats. Descriptions vary. Some portray it as an enormous fish, others as something more ambiguous. Modern analysis suggests these stories likely arose from sightings of large sturgeon, seals, or even drifting logs distorted by refraction in clear water. But once a narrative takes hold, it can persist. The lake's clarity may have contributed to such reports. When water is transparent, depth perception becomes distorted. Shadows appear elongated. Movements at depth look larger than they are. In low light, the mind fills in missing details. Stories of unusual creatures are not unique to Baikal. They appear around deep lakes worldwide. What distinguishes Baikal's legends is the context of its isolation and scale. Travel across Siberia historically involved long distances through forest and steppe. Reaching Baikal could feel like arriving at a world apart. In the 17th century, Russian explorers encountering Baikal recorded impressions of vastness and danger. They wrote of sudden storms and unpredictable ice. They also noted local reverence for the lake. As Russian settlement expanded, industrial activity reached parts of Baikal's shore. But even during the Soviet era, the lake retained symbolic status. Environmental debates surrounding industrial pollution in the late 20th century often invoked cultural respect for Baikal. It was not just an economic resource, it was a national treasure, deeply embedded in literature and identity. Poets and writers described Baikal with intensity, sometimes bordering on the mystical. Clear water became a symbol of purity. Depth became a symbol of endurance. Ice became a symbol of resilience. Yet beneath the literary language lay physical realities. Winds that could overturn ships. Depths that could swallow equipment. Ice that could crack under weight. Legends of spirits dwelling in the lake may have served as early frameworks for understanding risk. If one believed the lake had moods, one might approach it more cautiously. If certain rocks or capes were considered sacred, they might also be treated with care. Cultural narratives often encode environmental knowledge. For example, certain bays known for sudden storms might be associated with stories warning travellers away during specific seasons. Places where currents run strong might be linked with tales of hidden dangers. In this way, folklore can preserve patterns observed over generations. The Angara River, the lake's sole outflow, also features prominently in legend. Its steady current leaving Baikal contrasts with the many rivers entering. The story of Angara fleeing her father may reflect awareness of this imbalance. Only one river escapes, many join. Symbolically, it is an act of departure. Geographically, it is hydrology. The legend adds human dimension to water movement. Even today, visitors to Shaman Rock may see ribbons tied nearby. Though modern understanding of geology and hydrodynamics prevails, symbolic gestures continue. They coexist with research stations and monitoring equipment. The coexistence of science and legend does not represent conflict. It reflects layered understanding. Scientists explain methane bubbles as gas hydrate release. Photographers capture them as aesthetic patterns. Local storytellers may see them as signs of hidden life below. Each interpretation arises from different frameworks. The lake's reputation for mystery has sometimes attracted exaggerated claims. Stories of unidentified underwater objects, secret military experiments, or unexplained disappearances circulate periodically. In most cases, these stories dissolve under scrutiny. But their persistence underscores how environments that defy easy categorization invite speculation. Baikal's depth, clarity, and tectonic activity provide fertile ground for imagination. There is something about looking across a body of water that large and knowing it sits atop an active rift that stimulates narrative. Even the name Baikal itself is thought to derive from Turkic or Mongolic roots meaning rich lake or nature lake. Language carries perception. To call it a sacred sea rather than a lake changes expectation. Legends also reflect ecological observation. Seals breeding on ice, fish migrating seasonally, winds shifting with mountain temperature gradients. All these patterns became embedded in oral tradition long before formal documentation. In some tales, the lake is portrayed as generous when treated respectfully and harsh when ignored. That duality mirrors environmental reality. A storm that arises quickly can capsize a poorly prepared boat. Ice that seems stable can fracture under sudden temperature change. Respect is practical. In modern times, scientists working on Baikal often develop their own informal lore, stories of equipment lost to sudden wind gusts, of unexpected ice breakup during fieldwork, of submersible dives where visibility extended farther than anticipated. These stories are not mythic, but they contribute to collective memory among researchers. They reinforce caution and appreciation. The old Siberian waters hold both measurable processes and inherited stories. Hydrothermal vents and methane seeps exist alongside tales of spirits and serpents. Earthquakes underwater coincide with narratives of restless depths. The alien feeling described earlier intertwines with legend. When a place resists easy classification, stories arise to fill conceptual gaps. For the Buryat people, Baikal is not merely an object of study. It is ancestor, provider, and presence. For scientists, it is a natural laboratory shaped by tectonics and time. For travellers, it may be an experience of vastness and silence. Legends do not diminish scientific understanding. They reveal how humans historically responded to environments that felt larger than themselves. Standing at the edge of Baikal today, one can see research vessels moving across clear water, satellites overhead capturing data, and instruments monitoring seismic tremors. At the same time, one may notice ribbons tied to trees near sacred sites, remnants of rituals acknowledging forces beyond immediate comprehension. The lake accommodates both. It does not demand belief in spirits. It does not reject analysis. It simply exists deep and ancient. And as long as wind rises suddenly, ice groans in winter, and water stretches beyond sight, stories will continue to form around its shores, adding cultural depth to a basin already layered with geological and climatic history, reminding us that human interpretation, like sediment, accumulates over time in response to a landscape that has always felt slightly larger than explanation alone. During much of the 20th century, Lake Baikal existed not only as a scientific curiosity and sacred landscape, but as a site of strategic interest. The Soviet Union did not ignore a body of water that deep, that remote, and that geologically unusual. When people hear the phrase Soviet experiments connected to Baikal, imagination often moves quickly toward dramatic conclusions. Secret weapons, hidden submarines, unidentified objects lost in the depths. The reality is more grounded, but no less serious. Baikal's depth and clarity made it uniquely valuable for research that required extreme freshwater conditions. It was a natural laboratory contained entirely within Soviet territory, far from international shipping lanes and coastal surveillance. That mattered. One area of interest was deep water technology. Submersibles capable of operating at extreme depth had typically been developed for oceanic exploration. Deploying them in Baikal offered advantages. There was no saltwater corrosion to contend with. The enclosed basin reduced risks associated with open ocean currents. In the late Soviet and post-Soviet periods, the Mir submersibles conducted dives in Baikal, reaching depths over 1,600 meters. These missions were not military operations in the cinematic sense. They were scientific expeditions focused on geology, biology, and methane seeps. Still, the technology used had roots in broader deep-sea research programs that included military applications. Any nation capable of building submersibles that can withstand immense pressure inevitably considers strategic possibilities. Baikal also attracted attention for acoustics research. Because of its depth and water clarity, the lake provides distinctive sound propagation characteristics. In deep water, temperature and pressure create layers that bend sound waves. Understanding how sound travels underwater is important for submarine navigation, sonar development, and detection systems. Research into underwater acoustics in Baikal contributed to general knowledge in this field. That does not mean submarines patrolled its depths regularly, but acoustic studies conducted there informed broader understanding applicable in marine environments. The Soviet Union also maintained strong interest in seismology. The Baikal Rift Zone offered an accessible location to study intracontinental rifting and earthquake behaviour. Installing seismographs around the lake allowed researchers to monitor crustal movement. These installations were scientific in nature, but seismic data always carries dual relevance, for understanding geology and for assessing nuclear test detection capabilities. During the Cold War, monitoring seismic waves globally was critical. Distinguishing between natural earthquakes and underground nuclear detonations required refined instrumentation. Studying an active rift like Baikal helped calibrate those distinctions. There are also persistent rumours about submerged equipment or abandoned experimental platforms. Some of these stories stem from real infrastructure. Underwater cables, research stations, and moorings were installed at various times. Weather and ice conditions occasionally damaged or displaced equipment. Recovery at extreme depth is difficult and expensive. Objects lost to the lake floor may remain there indefinitely. In an environment where depth exceeds 1.6 kilometers, retrieval operations are not trivial. This has contributed to speculation about what might remain unseen below. Another area of Soviet interest involved neutrino detection. In the late 20th century, scientists established a neutrino observatory in Lake Baikal. This was not a military installation, it was a particle physics experiment. Neutrinos are nearly massless subatomic particles that rarely interact with matter. Detecting them requires large volumes of transparent medium. Baikal's clear water and winter ice cover provided ideal conditions for deploying arrays of photomultiplier tubes deep underwater. The Baikal Neutrino Telescope, located in the southern basin, has been operational in various forms since the 1980s. It is one of the world's first underwater neutrino observatories. The concept is straightforward in principle. When a high-energy neutrino interacts with water molecules, it can produce a faint flash of light called Cherenkov radiation. Sensitive detectors capture these flashes. Because Baikal's water is exceptionally clear, light can travel significant distances without excessive scattering. Winter ice offers a stable platform for installing and maintaining equipment. To someone unfamiliar with particle physics, the idea of instruments detecting flashes of light deep underwater might sound mysterious. In reality, it represents fundamental research into astrophysics. The neutrino telescope remains active, upgraded over time. It operates in collaboration with international research groups. Its presence reinforces Baikal's reputation as a site where unusual phenomena, both natural and scientific, occur beneath the surface. During the Soviet era, there was also interest in hydrology and water purity. Baikal's enormous freshwater reserves were recognized as strategically valuable. Studies examined water chemistry, inflow rates, and outflow dynamics. Understanding such parameters had implications for resource management. Although no large-scale diversion projects were implemented, discussions about utilizing Baikal's water resources surfaced periodically. Industrial activity near the lake, particularly the Baikalsk pulp and paper mill, created controversy. Environmental degradation risked damaging a globally unique ecosystem. Public protests and scientific advocacy eventually led to the plant's closure. In this context, secret missions sometimes refer less to covert operations and more to restricted research, conducted during a time when transparency was limited. The Soviet system did not freely disseminate all scientific findings. Research conducted in Baikal during certain periods was not immediately available to the international community. This lack of open communication fostered speculation. Some stories describe divers encountering unusual underwater structures. Most such accounts resolve into explanations involving research equipment, rock formations, or optical distortion. In extremely clear water, depth perception can be deceptive. Artificial light beams create stark contrasts. Objects half buried in sediment can appear larger or differently shaped than they are. There were also military training exercises in the broader region. Siberia hosted various defense installations. However, no verified evidence indicates that Baikal functioned as a site for large-scale secret submarine bases or exotic weapon testing. Its freshwater environment is fundamentally different from oceanic conditions required for naval deployment. What is true is that Baikal's remoteness provided privacy. Field stations could operate without intense external scrutiny. Cold War context meant that scientific and military research often overlapped in infrastructure and funding. Acoustic studies, seismic monitoring, and deep water engineering served dual-use purposes. From a modern perspective, much of that work appears ordinary within the framework of state-sponsored research during geopolitical tension. Yet the combination of depth, secrecy, and limited public information allowed myths to grow. There are tales of unidentified submersibles glimpsed briefly before disappearing into darkness. No credible documentation supports such encounters. There are claims of lost nuclear devices or classified experiments resting on the lakebed. Again, no verified evidence confirms these stories. But when a lake is as deep as Baikal and its bottom is visited infrequently, imagination fills gaps. The mere dives themselves generated media attention. Images of Russian submersibles descending into an inland lake carried symbolic weight. They reinforced the idea that Baikal was not just another freshwater body, but something requiring ocean-grade technology to explore. Each dive revealed sediment plains, methane seeps, and endemic life. They did not reveal hidden bases. Still, the image of a manned submersible sinking into Siberian depths was powerful. The neutrino telescope added another layer. To say that detectors are waiting in darkness for flashes from cosmic particles sounds abstract and technical. Yet it involves sensitive instruments anchored deep in a lake once described as bottomless by early explorers. Science in Baikal often sounds unusual because the lake itself is unusual. Soviet and post-Soviet research there reflects this uniqueness. The lake's role in particle physics, geology, and hydrodynamics places it at intersections of disciplines not typically associated with inland waters. Some former researchers have described fieldwork in Baikal during the Soviet period as intense and disciplined. Resources were limited but focused. Access to certain data required authorization. In that environment, even ordinary scientific missions could feel clandestine. Today, international collaboration has increased transparency. Data from seismic networks and neutrino observatories are shared globally. Environmental monitoring is coordinated with foreign institutions. Yet remnants of Cold War narrative linger in popular imagination. Part of that narrative is fueled by Baikal's characteristics. An ancient lake in Siberia sitting over a rift containing methane hydrates and hydrothermal vents, with underwater detectors searching for cosmic particles. Such a combination invites speculation. In reality, most Soviet-era activities in Baikal fall within the spectrum of scientific research common to large national programs. Seismology to understand crustal movement, acoustics to refine underwater detection, particle physics to explore fundamental forces, hydrology to manage resources. There were no confirmed secret underwater cities or classified alien retrieval operations hidden beneath the ice, but there were instruments lowered into darkness, engineers testing pressure hulls, physicists waiting for faint flashes of Cherenkov light, and geologists mapping faults beneath sediment. The secrecy was bureaucratic rather than fantastical, and perhaps that distinction matters. Because when a place feels alien, deep and remote, it becomes a canvas for narratives beyond fact. Baikal's role in Soviet research reflects practical interest in a unique environment. It also reflects the broader context of a time when science and state strategy were closely intertwined. The lake remains. The rift continues to widen millimetre by millimetre. Neutrino detectors still wait in darkness. Seismographs continue to record tremors. Hydrothermal vents still release warm water. Whatever missions took place in previous decades are now layers in a human history overlaying geological time. They add intrigue to the lake's story, but they do not redefine its nature. Baikal was ancient before any submersible descended. It will remain deep and active long after the last instrument is retrieved from its floor. And the notion of secret missions, whether exaggerated or mundane, ultimately speaks less about hidden machinery beneath the water and more about how humans respond to a place that already feels like it holds more than can be seen from the surface. Lake Baikal exists because the Earth's crust beneath it is being pulled apart. That pulling has not stopped. It happens slowly, measured in millimeters per year. Instruments anchored in bedrock on opposite sides of the lake confirm that the two sides continue to drift away from each other. Most days, this movement is imperceptible, but over millions of years, millimeters accumulate into kilometers. So a natural question emerges: what happens if the rift wins? To understand that, it helps to look at how continents break apart. The Atlantic Ocean did not always exist. Roughly 200 million years ago, the supercontinent Pangaea began to split. Rifts formed within continental crust. As extension continued, crust thinned and fractured. Eventually, magma rose to fill the gap, forming new oceanic crust. Seawater flooded the widening basin. The process transformed a continental interior into an ocean. Baikal represents an earlier stage of that sequence. It is a continental rift lake, similar in principle to the East African rift lakes such as Tanganyika and Malawi. These lakes occupy elongated depressions created by stretching crust. In Africa, geologists believe that if rifting continues long enough, the continent could eventually split, creating a new ocean basin. Baikal is part of a comparable system. The Baikal Rift Zone extends for more than 2,000 kilometers. It marks a region where the Eurasian plate is under tension. Current extension rates are modest, just a few millimeters per year. At that pace, dramatic transformation would require tens of millions of years. But geological time does not rush. If extension continues, the crust beneath Baikal will thin further. As crust thins, it subsides. Subsidence creates space. Sediment fills some of that space, but if extension outpaces sedimentation, overall depth increases. Eventually, if the rift widens enough and connects to an existing ocean basin, seawater could invade. That scenario would fundamentally transform the lake. Fresh water would mix with salt water. Endemic species adapted to freshwater conditions would face immediate stress. The Nerpa, Baikal's freshwater seal, would no longer inhabit a purely freshwater system. Golomyanka and other endemic fish might struggle to survive in changing salinity. But such a transformation is not imminent. There is currently no direct marine pathway connecting Baikal to the ocean. The nearest ocean lies more than 1,000 kilometers away. For seawater to reach Baikal, large-scale tectonic rearrangement would need to occur. One hypothetical pathway would involve continued rifting linking Baikal's basin with other rift structures that eventually connect to coastal regions. This would require substantial crustal reorganization. Another possibility is that rifting could stall. Not all rifts succeed in becoming oceans. Many rift systems initiate and then cease before reaching full oceanic spreading. If mantle heat diminishes or regional stress patterns change, extension could slow or stop. In that case, Baikal would remain a deep continental basin indefinitely. Geological evidence suggests that rift systems can persist in intermediate stages for tens of millions of years without progressing to full ocean formation. Baikal itself has already existed for approximately 25 million years. That is long enough for ocean formation in some cases. The fact that Baikal remains a lake indicates that rifting has not yet crossed the threshold into seafloor spreading. Seafloor spreading requires sustained magma upwelling and creation of new oceanic crust. Evidence beneath Baikal shows elevated heat flow, but not widespread active seafloor spreading. If the rift were to accelerate, signs would appear. Increased volcanic activity would likely precede ocean formation. More frequent or stronger earthquakes might occur. Surface uplift and subsidence patterns could shift. So far, data suggests steady but not rapidly accelerating extension. Still, imagining the long-term future clarifies the scale of processes at work. If, millions of years from now, Baikal were to become an ocean basin, the transformation would be gradual. First, widening, then increased subsidence, then possible intrusion of magma forming new crust. Finally, connection to a marine system. In that distant future, the current shoreline would no longer exist as it does today. Mountains flanking the lake might become coastal cliffs. Sediment currently accumulating in fresh water would give way to marine deposition. The endemic species that evolved over millions of years in isolation would face extinction or forced adaptation. Evolution would begin again under new conditions. That possibility carries scientific interest rather than immediate concern. On human timescales, the rift's continuation means something else. It means ongoing earthquakes. It means continued hydrothermal activity. It means subtle changes in basin geometry. If extension continues steadily, maximum depth could increase gradually. Sediment thickness would also increase. Baikal could become even deeper relative to surrounding terrain. Such deepening might influence circulation patterns. Changes in basin shape alter current pathways. Over centuries or millennia, these changes could affect oxygen distribution and nutrient cycling. However, compared to climate change over the next century, tectonic change remains slow. When scientists speak of the rift winning, they're not predicting sudden rupture. They're acknowledging that continents are not static. What appears permanent in human perception is temporary in geological perspective. The Himalayan mountains rise because India collided with Asia. The Atlantic Ocean widens because plates continue to diverge. Baikal deepens because Eurasian crust is under tension. Winning, in this context, means the continuation of a process already underway. There is also an alternative outcome. If regional stress patterns shift, perhaps due to distant plate interactions, the rift could become less active. Extension could slow to near zero. In that case, Baikal would remain a deep lake, but its tectonic future would stabilize. Sediment would continue to accumulate. Over tens of millions of years, sediment could fill the basin faster than subsidence deepens it. Eventually, depth might decrease. The lake could become shallower. This has happened to other rift basins around the world. Predicting which path Baikal will follow requires modelling mantle dynamics, regional plate forces, and long-term stress distribution. Such models carry uncertainty. Mantle processes operate beyond direct observation. Seismic tomography provides images of velocity variations beneath the rift, suggesting elevated temperatures. But translating those images into future scenarios involves assumptions. One measurable indicator is extension rate. GPS data show that widening continues, but whether that rate will increase, decrease, or remain constant over millions of years is unknown. From a biological perspective, the continuation of rifting shapes habitat. Deeper basins create pressure-adapted ecosystems. Hydrothermal systems create chemical niches. Earthquakes reshape sediment and release methane. If rifting intensified, ecological dynamics would respond. If it slowed, stability might increase. In both cases, change remains gradual. There is no scenario in which Baikal splits open dramatically within human lifetimes to form an ocean overnight. The scale of continental breakup defies cinematic pacing. It unfolds slowly, layer by layer. Still, awareness of tectonic motion adds perspective to the present. When standing on Baikal's shore, one stands above crust that is thinner than surrounding regions. That thinning continues. The lake exists because tension pulled the land apart. That same tension has not resolved. It is tempting to frame this in competitive terms, whether the rift will win. But geology does not operate in contests. It operates in processes. If extension continues, Baikal may one day be part of a larger marine system. If it stalls, the lake may persist for tens of millions more years. Either outcome reflects forces operating far beyond human planning. In the nearer term, the more immediate transformations come not from tectonics but from climate and human influence. Surface warming alters ice duration. Nutrient input affects clarity. Species respond to shifting conditions. These changes occur faster than crustal movement, yet tectonics underlies all of it. Without the rift, there would be no deep basin. Without depth, there would be no methane hydrates, no pressure-adapted amphipods, no hydrothermal vents, no freshwater seal isolated from the ocean. The rift created possibility. If it continues, it will shape possibility further, and so the question of what happens if the rift wins is less about dramatic endings and more about long continuity. It is about recognising that Lake Baikal is not a finished landscape. It is a stage in an ongoing geological sequence. Whether that sequence culminates in ocean formation or quiet stabilisation, the lake as we know it exists within a window of time. A long window by human standards, a brief one by planetary standards. For now, the water remains fresh. The basins remain enclosed. The Angara River carries water outward. Seals breed on ice. Scientists lower instruments into darkness. The crust continues to stretch. And far beneath the surface, stress accumulates slowly, shaping a future measured not in decades or centuries, but in millions of years, where the outcome of that stretching will eventually be written in rock, long after current shorelines have shifted and the present form of the lake has become part of its own sedimentary archive. Scientists are not easily unsettled. They are trained to measure, to quantify, to compare data against models and to separate observation from imagination. Most of what makes Lake Baikal extraordinary has an explanation. The depth is measurable. The rift movement is tracked by GPS. Methane seeps are mapped. Ice thickness is recorded annually. Species are catalogued. And yet, when researchers speak candidly about Baikal, there is often a tone that suggests caution. Not fear, not alarmism, but unease. It begins with scale. Baikal is not just the deepest lake. It holds roughly 20% of the world's unfrozen freshwater. That concentration alone gives it global significance. If something destabilizes Baikal's ecosystem in a major way, it is not a local event. It affects planetary freshwater balance. Large systems tend to be stable, but when large systems shift, the consequences can be wide. The unease partly comes from the recognition that Baikal's stability rests on several interconnected processes. Deep oxygenation depends on seasonal mixing. Seasonal mixing depends on temperature gradients and wind patterns. Temperature gradients depend on regional climate. Regional climate is changing. Surface water temperatures in Baikal have shown measurable increases over recent decades. Ice cover forms later and melts earlier compared to historical records. These are not catastrophic changes in isolation. They are gradual. But Baikal's ecosystems evolved under long-term stability. Episcura, Baikalensis, the tiny copepod responsible for much of the lake's clarity, thrives within a specific temperature range. If warming shifts seasonal cycles significantly, plankton dynamics may change. Even small shifts in plankton communities ripple upward through the food web. Golomyanka feed on zooplankton. Nerpa feed on Golomyanka. Sponges rely on stable chemical conditions. The lake's biodiversity is specialised. Specialisation reduces flexibility. Scientists have observed localised outbreaks of filamentous algae in certain shallow areas, particularly near urban settlements. These outbreaks correlate with increased nutrient input and warming water. So far, such events remain limited in scope, but they serve as indicators of vulnerability. There is also the issue of time compression. Baikal's sediment record shows that climate has shifted before. Ice ages came and went, temperature fluctuated, yet those changes occurred gradually over thousands of years. Modern warming is occurring within decades. Species that adapted over millions of years now face environmental change unfolding within a single human lifetime. That pace creates uncertainty. Another source of unease is tectonic. The rift beneath Baikal remains active. Earthquakes occur regularly, most are minor. But seismic risk persists. Underwater landslides triggered by earthquakes could disturb methane hydrates or sediment stability. Large events are rare, yet possible. The interaction between tectonics and methane storage remains an area of study. Scientists do not predict explosive gas release scenarios, but they acknowledge incomplete knowledge. Then there is the matter of methane itself. Methane hydrates beneath Baikal are stable under current temperature and pressure conditions. If bottom water temperatures were to increase significantly, hydrate stability zones could shift. Deep water temperatures have remained stable so far, but modelling long-term climate trajectories introduces scenarios that are difficult to validate with limited historical data. Baikal's depth buffers rapid temperature changes, but buffering is not immunity. Hydrothermal vents add another variable. Heat flow beneath the rift contributes to localised convection. If tectonic activity alters fault permeability, hydrothermal circulation could change. Such changes might influence chemical gradients that support microbial communities. The unease arises not from dramatic evidence of collapse, but from layered uncertainties. Each process, climate, tectonics, methane cycling, biodiversity, appears stable within certain bounds, but the bounds are not fixed, they depend on interactions. Baikal's uniqueness amplifies concern. If a common lake degrades, restoration strategies exist. Species may recolonize from neighbouring waters. If Baikal's endemic species decline, there is no external reservoir to replenish them. The Nerpa exists nowhere else. Hundreds of amphipod species exist nowhere else. Loss in Baikal is permanent. Scientists also feel unease because Baikal serves as a reference point. Its sediment archive informs global climate models. Its ecosystems represent long-term evolutionary stability. If Baikal begins to exhibit rapid change, it signals broader systemic shifts. In recent decades, researchers have documented alterations in plankton bloom timing. Warmer springs lead to earlier phytoplankton growth. This affects zooplankton reproduction cycles. Temporal mismatches between predator and prey can cascade. Such mismatches are subtle. They require long-term datasets to detect. Baikal has benefited from sustained monitoring, but even decades of data are brief relative to its history. Another concern lies in human pressure. Tourism around Baikal has increased. Infrastructure development introduces wastewater and runoff. While industrial activity such as the Baikalsk pulp and paper mill has ceased, legacy pollution remains in sediment near former discharge sites. Microplastics have been detected in water samples. Concentrations are lower than in many heavily urbanized lakes, but their presence indicates global reach. Because Baikal's water turnover time averages around 330 years, contaminants introduced today may persist for centuries. Slow flushing means slow recovery. That temporal inertia heightens responsibility. Scientists often express unease in probabilistic terms. They do not predict imminent disaster. They identify trends and confidence intervals. They model scenarios. The uncertainty ranges widen when projecting decades ahead. Climate models predict continued warming in Siberia. Projected temperature increases vary by scenario. How those increases translate into specific changes in Baikal stratification patterns remains partially modelled but not fully validated. Ice duration is one of the most visible indicators. Shorter ice seasons affect Nerpa breeding. Reduced ice thickness alters winter travel safety. Changes in snow cover influence under ice-like penetration. These shifts are measurable. They are not speculative. What remains uncertain is threshold behaviour. At what point does reduced ice duration significantly impact seal population viability? At what point does warming alter Episkura's filtration capacity enough to reduce clarity measurably? At what point do methane hydrates respond to bottom temperature shifts? These thresholds are difficult to define precisely. Large, complex systems often absorb change gradually until a tipping point is reached. Then shifts can accelerate. Baikal's long history suggests resilience. It has survived glacial maxima and interglacial warmth. It has endured volcanic ash deposition and tectonic pulses. But resilience in the past does not guarantee resilience under novel combinations of stressors. Modern warming combines with anthropogenic nutrient input, global atmospheric changes, and increased human presence. This combination has no exact precedent in the sediment record. Scientists are trained to avoid dramatic language, yet in discussions about Baikal, they often emphasize vigilance. Monitoring programs continue year-round. Temperature profiles are recorded from surface to depth. Seismic activity is logged. Plankton populations are counted. Genetic diversity studies track species health. This vigilance reflects recognition that Baikal is both ancient and delicate. The unease also stems from perspective. When you study a system that has remained relatively stable for tens of millions of years, you develop respect for its continuity. Seeing measurable change within a few decades can feel disproportionate, not because change is catastrophic, but because it contrasts with the long baseline of stability. There is also a philosophical dimension. Baikal embodies intersections of geology, biology, chemistry, and climate. It demonstrates how processes operating over vastly different timescales interact. Tectonics unfold over millions of years, climate shifts over thousands, industrialization over centuries, policy decisions over years, all converge in one basin. Scientists working there become acutely aware of these overlapping timescales. They measure millimeter per year crustal extension, while also tracking degree per decade temperature increases. They analyse sediment layers millions of years old while collecting water samples that reflect last season's runoff. This compression of timescales creates cognitive tension. The lake feels timeless. The data shows movement. There is no single factor causing unease. It is the convergence of many, an active rift beneath a globally significant freshwater reservoir, methane hydrates in sediment, unique endemic species confined to one basin, climate warming trends measurable within decades, human activity increasing along shorelines. None of these elements alone demands alarm. Together they require attention. Scientists continue to publish findings cautiously. They avoid sensational predictions. They emphasize ongoing research. Yet beneath that measured tone lies awareness that Baikal's uniqueness means its margin for error may be narrow. If the lake were ordinary, concern might be less pronounced, but Baikal is not ordinary. It is a singular combination of depth, age, biodiversity, tectonic activity, and climate archive. When such a system begins to show measurable shifts, even subtle ones, unease is a rational response. Not panic, not despair. Just recognition that an ancient equilibrium, maintained across millions of years, now exists within a rapidly changing planetary context. And in that recognition, scientists continue to measure, monitor, and analyze, aware that understanding Baikal is not merely about documenting what has been, but about watching closely to see how one of Earth's most extraordinary freshwater systems navigates a century of change unlike most of its past. If you stand at the edge of Lake Baikal long enough, the categories begin to fall away. It stops being only a lake. It stops being only a rift. It stops being only a climate archive, or a methane reservoir, or a habitat for species found nowhere else. It becomes something more difficult to define. You see the surface first. Clear water stretching outward, sometimes calm, sometimes folded into long steel-grey waves under sudden wind. In winter, a frozen plain reflecting sky so precisely that horizon lines blur. From shore, nothing about it suggests the complexity beneath. There are no warning signs posted along the water explaining that below you lies more than a kilometer of depth. No visible indicator that 7 kilometers of sediment record millions of years of climate history. No sign that the crust beneath is thinning millimeter by millimeter each year. The lake does not announce itself, and yet everything about it hints at scale. The air feels different near large water. Sound carries differently. Weather shifts quickly. Mountains framing the basin rise sharply, emphasizing how the land drops away beneath the surface. You know, because you have learned that hydrothermal vents release warm mineral-rich water in darkness below, that methane hydrates remain stable under pressure, that amphipods adapted to extreme conditions move slowly across sediment, that a freshwater seal raises its young on winter ice in the center of a continent. You know that earthquakes ripple through faults beneath the basin, that GPS instruments detect slow widening. That sediment accumulates year by year, adding thin layers to an archive already millions of years thick. Standing there, those facts settle into perspective. The lake appears still, but stillness is only surface behaviour. The rift continues, ice forms and fractures. Methane seeps upward in steady streams. Plankton bloom and fade with seasonal light. Scientists lower instruments into the dark. Tourists photograph bubbles frozen in blue ice. Local communities tie ribbons near sacred rocks. All of it coexists. There is a quiet humility in recognizing that Baikal has persisted through glacial cycles, volcanic ashfalls, tectonic pulses, and climate shifts long before modern observers arrived with sensors and models. And yet there is also awareness that current changes are unfolding at a pace the sediment record has rarely seen. Ice cover shortens, surface water warms, species distribution shifts subtly. These changes are not visible from a single glance. They appear in data sets, in time series, in graphs plotted over decades. But the lake feels unchanged in the moment. That contrast creates tension. On one hand, Baikal seems timeless. On the other, it responds to forces acting now. If the rift continues to widen for millions of years, the basin may deepen further or one day connect to a distant ocean. If climate continues to warm, surface conditions may alter mixing patterns and biological cycles. These futures are not dramatic endings. They are extensions of processes already underway. Standing at the shore, it becomes clear that Baikal is not a finished object. It is a phase, a long phase, measured in geological time, but still part of an ongoing sequence. The water beneath reflects sky. Clouds move across it. At night, stars appear both above and in winter, below in ice reflections. Light and dark alternate with season. Nothing about it suggests urgency, and yet researchers continue to measure, not because they expect sudden collapse, but because understanding requires attention. Baikal has always changed. Sediment layers prove that. What is new is the rate at which some variables shift. The Unease scientists express is not fear of the lake itself. It is awareness that this ancient system now exists within a global context, shaped by rapid atmospheric and environmental transformation. When you look across the water, you cannot see methane hydrates, you cannot see fault lines, you cannot see diatom shells settling toward the bottom, you cannot see neutrino detectors waiting in darkness for faint flashes from cosmic particles. But all of it is there, layered, interconnected. If you remain long enough, the wind may rise without warning. Waves may build quickly across open water. In winter, a crack may split the ice somewhere in the distance, echoing across the frozen expanse. These sounds and movements remind you that the lake is active, not dramatic in everyday life, but never inert. Standing at the edge of the deep is not about confronting danger. It is about scale, about recognizing that beneath calm surfaces lie pressures and histories beyond immediate perception, about understanding that even the most ancient freshwater basin is part of a planet still reshaping itself. Baikal does not terrify because it hides monsters or secret machines. It unsettles because it compresses extremes into one place. Extreme depth in freshwater, extreme age in a dynamic rift, extreme biodiversity within isolation, extreme clarity overlaying tectonic strain, and all of it continuing. The rift stretches, the ice breathes, methane forms and dissolves, species adapt, data accumulates, sediment settles, the lake remains. If you leave the shoreline and travel away, the image stays with you. Not as a single fact about depth or age, but as a reminder that Earth's most remarkable systems often appear quiet from above. That complexity does not always announce itself loudly. That ancient does not mean static. Lake Baikal will continue to widen slowly beneath its surface. It will continue to hold water older than most civilizations. It will continue to preserve climate records in mud and support life found nowhere else. And somewhere below, in darkness under pressure, processes will keep unfolding whether observed or not, while at the surface, waves will keep folding and unfolding against the shore, indifferent to how long anyone stands there trying to understand what it truly means to face something that deep.